Hello everyone, welcome to the complete course on statistics and probability by Scalar. I, Sumit Shukla, will guide you through a complete new journey on statistics and probability in this particular course. We will be talking about Introduction to Statistics, Descriptive Statistics, Probability, Random Variables, Probability Distributions, Inferential Statistics, and Hypothesis Testing. But before we start, don't forget to check out Scalar's free masterclass on Scalar's event page by industry leading experts. The link is in the description box. Welcome to the first module of Statistics and Probability full course. In this particular video, we'll be talking about Introduction to Statistics and Descriptive Statistics. We'll be also talking about measures of central tendency and measures of variation. So let's get started. So let's start with, first of all, talking about statistics. Now, if we talk about statistics is broadly classified into three major categories. So let's discuss about them. And I will be writing all these notes. So if you feel like increasing the speed of this particular video, you can do that. But I'll be going in my very normal pace. So you can just adjust your speed about this video as you like. So statistics, the very first category is descriptive statistic. Then we have inferential, and finally hypothesis. We'll be looking at all these three segments in a very detailed way, but let's start by understanding a little bit about each of these categories. So we will briefly talk about what is descriptive statistics, what is inferential, and what is hypothesis. Let's first take some random data. Let's say we have this kind of data. So we have the data of, let's say, few students with their student ID, the name of the student, their marks, and let's say their age and from which city they belong to. So for a student ID, I'll just write SID, then name, marks, age, and city. And let's say we have few data points. Let's fill these tables with some random data. So 01, 02, 03, and so on till 0. Let's say we have some 1000 students. So 1000, name is, let's say, Sumit, maybe Ravi, Sanju, and Ankita. Then we have marks, let's say 100, 95, 82, maybe this is 60. Then age, let's say 29, 28, 25, and 30. City, so I am from Kanpur. Then Ravi maybe from Bangalore. Then maybe this is Chennai. And finally Ankita from, let's say, Jamshedpur. So we can just write Jamshedpur. Okay. Now, given this particular data, we have to understand this data. So if your manager, or maybe let's say the principal of a particular school, is asking you to summarize this data, now you will not be able to provide the information regarding each student, right? So you will not be going to your principal or maybe the head of the school to explain the person that, okay, we have Sumit, we have Ravi, we have Sanju, we have Ankita. The marks of Sumit is 100, the marks of Ravi is 95, the marks of Sanju is 82. It will take a lot of time, and it is also not feasible. And the head of the school will not be having this much time to listen to all your information. So what he or she is looking for? He or she is looking for some information that can fully describe the complete class. So what is the metric that we can use to consolidate or to better describe the complete class is what descriptive statistics is. For example, I can say that this particular class is having number of students as, let's say, 1000. Now this is a statistic which is describing the class, and hence descriptive statistic. Let's say the average marks of this class is 85. Again, this number, just this one number, is describing the complete class, and we will be talking more about what average is, but this number is talking about the complete class, and hence this is a descriptive statistic. For example, let's say the average age is, let's say 25. Similarly, maximum marks, then we have minimum marks. So all these numbers which describe the data in such a way that we just need this number to explain the complete data points is basically known as your descriptive statistics. It's very simple to understand, right? Now we have descriptive statistics can broadly be classified into two kinds of measure. So I'll just change my color and we'll write over here. So one is known as measures of central tendency, and then we have measures of variance, or you can say it is measures of variation. So I'll just simply write it as measures of variation. Okay, so we will be talking in detail about what are the various measures of central tendency is and what are the measures of variation is. So what we have learned regarding the descriptive statistics, it's basically those metrics that can define the complete data, or that can help us define the complete data. We do not need to look into each and every row. We do not need to look into each and every information. Remember, in a particular data which is cross-sectional, having rows and columns, each row is known as the information. So using the power of descriptive statistics, we do not have to go through each and every information. We can just use these metric to describe the complete data, right? Then we have inferential. Now, how we can understand inferential? So I'll just quickly change the color and we'll take one example. Let's say that is company, let's take any name of the company. Let's say there is a company known as Scalar. Now Scalar wants to know on an average how many hours a student is studying in 12th class. So what's the question? How many hours a student studies when the student is in 12th class. So I'll just write in bracket 12th class. Now if I look into this problem, overall there will be millions of students in India, right? And if I just limit my scope of study to India itself, so there will be a lot of students that will be present in India right now, those who will be in 12th class right now, right? And it is impossible for any company to perform survey in such a large scale. So let's say if Scalar has to get this number, Scalar has to basically get an average number. So I'll just write average. How many average hours? So how many, or maybe just simply write it as what's the average number of hours. So what's the average number of of hours a student studies in 12th class. In order to find this answer, how we will take the procedure or how we will take the approach. So let's say this is my complete population, all the students who are in 12th class this year. So 12th class students. Now there will be so many students, right? If I just have to take a number, let's take there are 100 million students. I'm just throwing a number. So 100 million students. In order to get this statistic, which is what's the average number of hours, I have to reach out to each and every student. So let's say the entity scaler is performing the survey. They will reach out to each and every student. They will ask the student whether the particular student studies for 1 hour, 2 hour, 3 hour, 4 hour, or maybe n hours. Then we will collect the data. The scalar team will collect the data. So let's say we have the data of student number 1, student number 2, student number 3, and so on till student number 100 million. Now once we have this data, we will take the average, and that is basically my output that I'm looking for. Now if we practically look into this procedure or into this problem, seems like this is practically impossible, because it is practically impossible for any company or individual to reach out to these many people or to reach out to these many observations or entities or individuals. You can call it anything, right? If even it is possible, it requires a lot of time and lot of money, lot of investment. So what are the practical problems? Number one, a lot of investment, a lot of time investment. Similarly, a lot of cost investment, a lot of cost investment. So we have to invest a lot of things, and none of the companies having this much time. So what is the practical solution for this? Well, the practical solution is very simple. What we are going to do, we are going to take some few students which we call as the sample, and we will also talk about how the sampling is performed. When we will be discussing about inferential statistics, we'll be talking about how sampling is performed. So let's say we are having a simple random sample, and the term simple random sample I'll be explaining you in a better way, so don't worry. So let's say we are having a sample. I have taken some random students. Let's say we have taken 100 students from Uttar Pradesh. We have taken 100 from, let's say, Andhra Pradesh, 100 from Tamil Nadu, 100 from Delhi NCR region. So like this, we have created a sample, and let's say this sample is having around 1 lakh student, 1 lakh. Now, in order to perform survey on 1 lakh people seems quite practical, right? We can perform the survey on 1 lakh people. So let's say after performing the survey on 1 lakh people, we have the data with us, S1, S2, and so on till S1 lakh. And now we can take the average. Once we have the average, this is known as the sample average. So I'll just write mu. Mu is a Greek letter which is commonly used to represent average. So average, then I'll write S, sample average. I'll just write it in brackets also, sample average. Now, inferential statistics is a branch of statistics which deals with approximating the population average or population parameter. Remember one thing, if I am talking about the average of population, it is population parameter. If I am talking about the average of sample, it is sample statistic. So there is a difference. So please remember, when I'm When I'm saying a statistic, I'm basically talking about sample, because practically it is impossible to do anything on population. There are two problems. Either we are not able to reach out to all the observations in the population. So if I ask you, find out the average height of Indian men. Now it is impossible for any individual to reach out to each and every Indian male, right? So that's basically my population, and if I can get that number, if I can get the average age of all the Indians in this, all Indian males from India, then that is known as the population parameter. Okay, so inferential statistics, coming to our point, inferential statistics is a branch of statistic which help us to perform approximations. So using this sample statistic, I will try to approximate the population parameter. So let me just quickly write it over here. Using sample statistic, we will try to approximate the population parameter, and that is basically known as the inferential statistic. Now there are some procedures, we have some few formulas, we will be talking about that, but this is basically the brief idea behind why we need inferential statistic. Okay, the last portion, or maybe the last segment, which is known as the hypothesis testing. When we talk about hypothesis testing, as the name suggests, we are trying to test something. Now what we are trying to test? We are trying to test something which has been proven, or maybe a claim, or maybe an statement. There can be anything that we are trying to test. Let's take one very general example. So you guys would have watched this Dettol advertisement which says that Dettol kills, or Dettol soap kills 99.9% of the germs, right? Now let's say you are suspicious about it. You are suspicious. You wanted to test whether this claim or statement made by the Dettol company, is it having some statistical significance or not? Is it statistically correct or not? And that is where the power of hypothesis testing comes into picture. So we will try to test here. We perform test to check if a particular claim or statement can be statistically proven. Can be statistically proven. So these are the three major segments which we are going to discuss. Now before we jump into any of these segments, we have to understand what kind of data we are working with. So we will be briefly talking about how we can explain a data. And when I say explain a data, what are the various types of column or variables we get in a data. So let's talk about it. We will be taking one very random example. So let's just quickly create a data. Again, we can extend the same example that we have taken in the last slide. We were having student ID, the name of the student, salary, age, or instead of salary, let's put marks, age, then city. Then we can go about writing grades and maybe subject, and finally we can talk about the gender. Let's fill this table with some few data points. So let's say we have 01, 02, 03, 04. Name is Sumit, Amit, Ajay, Ankita. Marks is, let's say, 89, 98, 95 and 62. Age is 29, 28, 25 and 30. City is, let's say, K and P, B and G, R and C, and let's say T A T A. Then grades A, B, C and B. Subjects, so let's use S1 as subject number 1, S2, S1, S3. Gender, male, 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 female. Now this is my dummy data. Now if I ask you, are you guys able to observe any kind of distinction among all the kind of variables that we are having in this data? So remember, these columns are also known as, the variables. So I may be using the term variables or columns, and as I have told you that each row is basically my group of informations. So each row is my information. Now if I carefully observe marks, age, these two columns are my numerical columns. And why I'm calling it as numerical? Because the data which these columns are holding are the numbers. These numbers are something that lies between a minimum and a maximum, right? So marks can be between 0 to 100. Age can be between, let's say, so since it is a school, let's take 25 to 35. Then if I talk about city, grades, subject and gender, all these are my categorical columns, categories, because city is having Kanpur, Bangalore, Ranchi, Tata. These are all categories, right? Grades A, B, C, D, categories. Subject S1, S2, S3, categories. Gender male, female, category. Similarly, this name is a categorical column because each name can be termed as a category. The student ID is a identity column. It is neither categorical nor numerical, so I can just simply call it as an identity column. Now there are in order to better explain these columns, we have a formal name given to all the numerical columns and all the categorical columns. Let's talk about it. So when we talk about variables, it is formally divided into qualitative and quantitative. Now, qualitative data is basically those columns which consist of non-numerical data. So columns which consist of non-numerical data. That's basically my qualitative data. Quantitative data is those columns which consist of numerical data. So simply I'll write numerical data. Numerical data. Now, within qualitative, there is a further distinction, which is your nominal and ordinal. Now, what is nominal? So, when we talk about nominal, these are those columns which consist of categories that does not comes with any kind of order among the categories. For example, I'll first take example. For example, city. Let's say there is a column city and the column is having categories as Kanpur, Delhi, and then Mumbai and Kolkata. Now, I cannot say that Kanpur is better than Delhi, Mumbai is better than Kolkata, because these are four distinct categories. They do not have any kind of orderness among them. So this is simply the nominal categorical variable or nominal qualitative variable. So I'll just write down the definition. Categories that does not follow order among them are basically known as nominal data. Ordinal data, you guys would have already guessed it. It is basically those categories that follow orderness among them. For example, grades, or for example, if I say grades is the best example. So grades, so grades can be A plus, or maybe I should write A plus first, or let's take A B C D. Now we know that A is better than B, B is better than C, C is better than D. So there is some orderness among these categories, and that's the reason ordinal data. We can also talk about class, like first class, second class, third class, fourth class. So there is orderness. If I talk about, let's say, your educational qualification, so let's say a person is graduate, a person is postgraduate, a person is intermediate. So I know that high school, then we can have intermediate, then we can have graduation, and then post graduation. So these are the four categories which will definitely have a order among them. So these are known as the ordinal qualitative variables. Now quantitative, as the name suggests, these are those variables which can be quantified. Quantitative means quantified. We can extract some quantity out of it. For example, minimum, maximum, we can perform addition, subtraction. So we can apply all those mathematical operations on these columns, and after applying the mathematical operations, the value will still make sense because they are quantitative. Now, quantitative are further classified as number 1, discrete and continuous. Now, when we talk about discrete, now these are those quantitative variables which will have values that cannot take decimal values, or that can only take integer or natural numbers. For example, number of students in a class. Now we know that a class can have 2 students, 3 students, 4 students, 100 students, 200 students, but a class cannot have 22.57 because this practically does not make any sense, right? So this is discrete quantitative variable. Similarly, number of citizens in a country, again, it will always be a natural number, which is countable and finite. So I'll just quickly write it in a bracket, countable and finite. When we talk about continuous, these are those variables which are non-countable or uncountable and infinite. Uncountable and infinite. Let's take an example and it will make better sense. For example, let's take income. Now, income of a person can lie between a minimum and a maximum value. For example purpose, let's take the minimum income is 100. The maximum income is, let's say, 1 million. Now, between these two numbers, I have infinite number of observations that are valid. Can a person earn, let's say, 100.15? Let's say these are in dollars, so it will make more sense. So is a person earning 100.15 a valid income? Yes. Is a person earning, let's say, 1 million, or let's take a smaller value so that you guys can understand it. So let's say 1265.778. I'm going very I'm taking more decimal values just to make you guys understand that this is also a possible value which can exist and which is practically possible. So a person can earn this number also, right? So between 100 and 1 million, I have endless possibilities, and each possibility or each observation is possible to exist. Similarly, we have age. Now let's say our minimum age is 27, maximum age is 35. Can I have a person with the age 27 years, 5 months, 6 days, 4 hours, 5 seconds, 6 milliseconds, 7 nanoseconds? Yes, practically possible. So at every nanosecond, I can have a particular observation that can lie in this scale. And that is the reason age is also a continuous quantitative variable. If I go back to my example, we can see that both marks and age, they are your continuous quantitative. Similarly, if I look into grades, they are qualitative, but it is ordinal. Then subjects, they are qualitative, but it is nominal. Similarly, grades, gender, qualitative, nominal, because I cannot say male is better than female or female is better than male. So these are two categories and it is nominal. City, again qualitative, nominal. So I'll just write Q-N. So name, again qualitative, nominal. And I have already told you that so student ID is basically an identity column. It is neither qualitative nor quantitative. So this is how we describe our data into various types of variables. Now we are going to talk in very much detail about what are the various measures of central tendency is and what are the measures of variation is. So with this particular topic, we will initiate the first category or maybe first group of discussion or first branch of our discussion, which is talking about descriptive statistics. Now let's try to understand what is descriptive statistics. As we have discussed previously, that descriptive statistics is all about describing the data in one number or in few statistics parameters in such a way that it can describe the complete information. And if I go back to my first slide, here you can see that I was having the data of some students, their name, marks, age and city. And if the principal of this following school ask the teacher that, okay, tell me how your class looks like. Now the teacher will not be taking the principal to each and every row or each and every information or each and every detail of the student. So let's assume that if I am one of the teacher, I would not say my principal that, okay, I have a class who is having Sumit, whose age is 29, whose marks are 100. And then we have another student whose name is Ravi, he is from Bangalore, he's 28 years old. As you can see that it will take a lot of time, and I would not be getting a complete picture of how my class looks like, right? And that is the reason we have these descriptive measures. And as we have discussed before, the descriptive statistics measure are broadly classified into two buckets. Number one is measures of central tendency and measures of variation. So let's try to now deep dive into these two particular topics. So descriptive statistics. As we already know that we have two measures of central tendency, and then we have measures of variation. You can also say it is measures of variance or variation. To be in general English, we can call it as measures of variation. Now what is measures of central tendency? As you know that if you carefully read the name, it says measures of central tendency. We are talking something regarding the center. Now, is it the center of the data or is it center of all the observation? Let's try to understand. Before we can quantify, before we can find out any of these measures of central tendency, we need some data, right? So let's create some hypothetical data of a class, and we have age. So let's say we have age of some 10 to 15 people, and let me just throw some numbers on my screen. So 24, 23, 26, then 21, 26, 27, 28, then one more 28, one more 28. Okay, let's make it as 26, then 32, 26, 29, and finally 28. This is the data I'm having. Please remember, each data point over here describes a particular student. So here we have a student number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13. So we are in total having 13 students in our class. Now how I can explain the complete data in one number? Well, we would try to extract that particular number which lies in the center of the data, so that we know that below this number, so assume that this pen is the center of the data, so I know that below this point I'm having few observations or few students, and above this point I'm having few students, and it will give me a better idea about how my data looks like, right? And that is what the measure of central tendency is. In this particular data, the very first measure of central tendency is the mean or the average, and many of you would have used it already. So mean, or also known as the average. Now I hope you guys already know the formula. If you don't know, it is basically the sum of all the observations divided by the number of observations. Mathematically, we can write it as summation of, so this is a Greek letter again, summation. I'm taking a summation over over S, and S is nothing but my student number, so SI, or just write it as SI divided by N. So if I expand this, it would look like this: S1 plus S2 plus S3 and so on till S13. This is my sum of all the observations divided by N. Now here you already know that we have 13 students, so divide by 30. If I solve this, so I have already done the calculations just to save some time, but if you want, you can pause this video, do the calculations, and I would suggest all of you to please have a pen and paper with you while you're watching this video, so that you can also fully understand the complete concept. So please watch, please stop the video, please pause the video and calculate it by yourself. If you have already calculated it, it is basically 26.46. Now this is the average age. What is the meaning of average? Assume that I have a number line. Now in this number line, this point 26.46 is lying at the center of the data, or maybe at the center of the number line. Now it might be at exactly center, it might not be exactly at center, but moreover it will be around the center. So assume that this is this particular data point, which is nothing but average, and average can also be written as X and this bar. So if you put X and over it or above it you put a bar, it's also known as X average, or we can call this as S average, because here we have assumed that this list is S. So this particular number is my S average. Now what we can understand from this number? We can understand that below this point I'm having few observations. Above this point I'm having few observations. Now you already know that in the class I'm having 13 people. So what we can conclude? We can conclude that in the class of 13 students, we have few students above the age of 26, and I'm just taking 26, and few students below the age of 26. So we are having few students above 26 and few students below 26, and this 26 is basically describing the center of my data. Now it might be exactly the center, it might not be exactly the center. Why? Let's try to understand this. Let's say given this data, I intentionally add a particular observation. So let me add one particular observation, 40, or let's add 50. So I'll write it over here, and maybe let me change the color, 50. So I've intentionally added a student whose ID is 14, and the age of this student is 40. And even if you look into this particular data, which is having 13 students, you can see that almost all the students are having age in 20s, which is 21, 22, 23, 24, till 29 we have a lot of observations, but there is one student whose age is 32, right? Now these observations are basically known as outliers. Let me just remove this particular data point, and let me write them in ascending order, and that would actually help us to derive the another measures of central tendency. So I'll write age is equal to, now the minimum number over here is 21. So I'll just draw a line over here, 21. Then we have, so we don't have 22, so we have 23. So I'll write 23 over here. Then we have 124. So 124. Then we have, I don't think we have 25. So no 25. We have 126, 226, 326 and 426. So 26, 26, 26, 26. Then we have 127 and only 127. Then we have 28, 28, 28, 28, 28, 28. Finally, we have 129 and 32. 29 and 32. So all I have done is just rewritten all the age of all the 13 students in ascending order, where this is the minimum age and this one is the maximum age. Now if you carefully observe, you can see that 32 appears to be very different from majority of the data. Now this observation is known as the outlier. So this is known as outlier. The formal definition of outlier is that particular observation in my data which is very different from majority of the data points. So let me just write it down. Outlier is that particular observation in the data that is very different from majority of the data points. So if you carefully observe, here majority of data points belongs to 20s, 21, 22, 23 till 29, but suddenly there is a number 32, and that is basically the outlier. Now what is the problem behind this outlier? Why outliers are problematic when we talk about the descriptive statistics? If I try to look at the median, now what is median? Median is another measure of central tendency. So what is median? Median is another measure of central tendency. So we have already talked about mean over here. Then we have median. Median is exactly the center of the data, exactly center. When I say exact center, that basically means above this I will have 50% people, below this I will have 50% people. So it is exactly the center. How we can find out median? So there is a simple formula, n plus 1 divided by 2 if the number of observations are odd. Here we have odd number of observations, 13. So 13 plus 1 divided by 2 is 14 divided by 2, which is 7. So my 7th observation is the center of the data, or is the middle point of the data. And let me just quickly mark it. So it is 1, 2, 3, 4, 5, 6, 7 over here. This is my center. Now if you just number, if you just calculate, if you count below this 26, below this middle point, I'll just write M to depict that this is a middle point. I am having 1, 2, 3, 4, 5, 6. I'm having 6 observations. Above this 1, 2, 3, 4, 5, 6. I'm having 6 observations. So median describes the exact center point of the data. So what is median? This value lies exactly in the center of the data in such a way that we have 50% observations above this point and here we have taken M, so above this point M, and 50% observations below this point, and again this is M, so below this point M. So median describes the center of the data in such a way that it is lying exactly at the center, where 50% of the data is below this point, 50% of the data is above this point. While I cannot say the same thing for average, and you can see why. Average is basically taken out by considering all the data. When I have to calculate average, I am summing over all the data. Here you can see the formula. The formula is sum over all the data points divided by the number of data points. And due to these influential observations, which are known as outliers, my average can shift towards the outlier. Here you can see mean, as I have told you, mean is also the center of the data, while median is also the center of the data. These both metric describes central point of my data. But why there is a difference? Why my average is 26.46 and why my median is 26? So my median is 26. Now this is because of this outlier. So where I'm having outlier on the higher end. This is my higher end. So what has happened to the mean? My mean has also shifted towards the outlier. Now please remember this. I'll just write down as a note over here that your average gets impacted with the presence of the outliers and will shift towards the outlier. So if my outlier, so assume that if this is my number line and if my outlier is on the lower side, then my average will shift towards the outlier. So my average will shift towards the outlier. If my outlier is on the higher side, then my average will shift on the higher side. And we have already seen this example. My median was 26, but my average came out to be 26.46 because my average has shifted towards the outlier, right? Then we have one more measure of central tendency, which is mode. And mode is very simple to understand. Mode is the observation with the highest occurrence in the data. So let me write the definition over here. I'll just simply write it as observation with maximum frequency. Observation with maximum frequency. So if you carefully observe in this particular data, I'm having the observation number 26, not number 26, observation 26. This observation has appeared for 4 times, right? So the frequency is highest for the observation 26, and hence my mode of this data is 26. Mode of the data is 26. Now there might be cases where you do not have any mode. For example, let's say I'm having 4 observations 26, or there are 4 students with the age 26. We also have 4 students with the age 28. Now in that case, when there is a tie or there is no mode, so you will simply write no mode. In that case, you have to use mean and median to describe the center of the data. So I hope you guys are able to understand the measures of central tendency. As the name says, this or all these three measures, which are mean, median, mode, they basically describe the center of the data. And if your data does not comes with outlier, and here you have seen that 32 was the outlier, but if your data does not comes with outliers, maybe either on the higher side or on the lower side, we do not have any outlier, then these three measures will fall very close to each other, or approximately they will be equal to each other. So your mean will be equal to mode equal to median. And here you can see I was having average to be 26.46. If I was not having this outlier, which is 32, I would have got this value close to 26 only. Sorry, 26.46 is my average. My median is 26. My mode is 26. In this case, I can say that my data is having a center of 26. Now, if I go to my principal and if I tell to my principal that the average age of my class is 26 with 13 students, then it gives the rough idea to the principal that okay, we have a center point 26 and we have few students above this point, few below this point. If I tell to my principal that the median is 26 with total number of students to be 13, then in that case the principal will be able to do a little bit of math and he will be able to understand that okay, we have 6 students below 26, 6 students above 26. So I hope you guys are clear with measures of central tendency, but there is a problem. The problem is I'm still not clear how the values are varied. So I know that center is 26, but how the variation is there in the data. So am I having the age of the students to be very much varied? When I say varied, that basically means the values are very, very far away from the center. So let me just give you a very simple example over here. Let's say this is 26. This is 26. And here also we have 26. So in these two number lines, the center is 26 itself. But in this number line that is on my left of the side, left of my screen, the minimum is 15, maximum is 30. Here you can see that the minimum is 20 and maximum is 30. Or let's take it as 29. Now here if you see that the values are very far away from the center, there is a high variation, while here the values are not so far away from the center, the variation is low. So measures of variation tries to quantify this variation. Given a particular data, how much values are scattered around the center. This is what we are going to learn in measures of variation, which is our next topic. So now let's talk about measures of variation. Measures of variation. And I have already given you a very short example, I would say, in my last slide. But now let's try to have a more insightful example which will clarify your doubt regarding what exactly is measures of variation. So let's try to take two examples or two subjects, and I'm just plotting these two subjects to get you a visual picture about what exactly I'm trying to explain. Assume that here the x-axis represent the student ID for both the plots and y-axis represents the marks. These are the marks. So let's say the average marks are represented by this red color line. red color dotted line. These are the average marks, or this is the average marks. For example, you can assume that the average marks is 50 for both the subjects. But for subject A and this is subject B, I'm not just naming any subject, I'm just saying A and B. For subject A, the student marks are scattered like this. So this represents the marks of student number 1. So this is student number 1. Then this marks of student number 2. Then we have student number 3 and so on. So I'll just draw it now because I hope this gives a clear picture about what I'm trying to explain. So this is basically the scatter plot for subject A. For subject B, this point represents the marks of student number 1, this for student number 2, then 3, 4, 5, 6, 7, 8 and 9 and let's say 10. Here also I think we have 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see that, and in both A and B we are having 10 students. But for subject A, you can see that all the marks or all the students have scored, they have scored marks which are very close to the average. Most of the people have scored, let's say, if I just create a band, let's create this band, a dotted band. So most of the students fall in under this band or within this band. While here for subject number B, you can see that there is a lot of scatterness. You can see that there are data points which are very far away from the average line. There are data points which are also close to the average line. But in subject A, all the data points are very closely scattered around the average line, right? Now, can I say that for subject A, the variation around the mean, so this is my mean, the red color dotted line is my mean or the average line. So M represents the mean or the average line. So for subject A, the variation of the marks around the mean is low. For subject B, the variation of marks around the average line is high. So here, variation around the average line for subject A is low, while for this, variation around the average line for subject B is high. Now the measures of variation tries to quantify this. How I can say this is low and how I can say this is high? We need a number, right? We need some quantity. We need a number that can describe this measure or describe this scatterness or describe this variation. So measures of variations are those metric that describes the variation of the data around the center or around the average line. So measures or metric that describes the variation of the data around the center of the data, center or the average. Now what all measures we have? So number one, so I'll write it over here. We have, so we exactly have, I think, 4 measures. Let me write it down. So we have range, we have variance, we have standard deviation, and finally we have the coefficient of variation. So let's talk about each of them. Now in order to talk about any of them, we need the data. So let's create some random data. So let's say here we have the data of the marks of a student in one particular subject. And I'm intentionally drawing this table a bit large because we will be calculating a few parameters in order to arrive to the exact quantity that we are looking for. So let me just quickly draw the table. So here we have the student ID, which again runs from 1 to, let's say, 10. 1, 2, 3, 4, 5, 6, 7. Then these are the marks. So I will write XM. XM means marks of students. So let's say the marks are 27, 52, 48, 30, 33, 39, 65 and 82. Now this is my marks of the students. Now if I have to calculate the range is nothing but the maximum minus minimum. It gives you a very raw idea regarding what is the range of my what is the range at which we are trying to work, or if we are talking about the marks, then what is the minimum marks scored, what is the maximum marks scored, and the range is nothing but the difference between max minus min. So my max marks is 82 minus minimum, which is 33, and if you subtract this you will get the range. The second measure is variance, which is a better measure to define the variation in the data. What is the problem with range? Range is again influenced by the outlier. So let's say if there is one student in the class who has scored 100, while most of the student has scored, let's say, close to 33, 35, 39, 40, then in that case also the range would be very high. So it would mislead you. It would give you a misleading idea that students have scored in a high range, but that is wrong. Range gets influenced by the presence of outlier, and that is the reason we don't use range as a measure to make or to understand about how the data is scattered around the center of the data or center line. So let me write it down over here. Range is a metric that gets influenced with the presence of outlier. Now how to arrive to the variance? So we are talking about variance now. In order to calculate variance, we will first of all find out the center, because as I have told you, variance is all about calculating the scatterness or calculating the variation of the data from the center point, which is the mean or the average. So we have to find out the average first of all, the average. And if you guys want, you can pause this video and quickly calculate the average, because we have already learned about it. So just take the sum of all the observation divided by 7, because 7 is the total number of students in the class, and that would give you the average. So the average of this particular marks for the students would came out to be 49.42. Now for simplicity purpose and for making all the calculations very simple, very clean, let's take this number as 49. So assume that the center is 49. Now we have the center. So let me just quickly draw the graph. The same graph that we have seen in the last slide. This is a student ID. These are my marks. And we have the center now at 49. So somewhere in the middle, but 1 point below. So assume this is 49. So this is my 49. Now let's mark all these numbers. So 27 would lie somewhere around here. So this is student number 1. Then we have 52. So this is my student number 2. And then we have 48, which is very close to the average. So this is 48. Then 33, somewhere over here. 33, then 39, maybe over here. Then 65, over and above the average line. And finally 82, which is again over and above the average line over here. So these are my data points. This is my student number 3. This is 4, 5, 6, finally 7. We have 7 data points. Now we will calculate the distance of each of this data point from the center which is average. So when I say distance, I am basically interested in this distance. This is D1, then this is D2. Similarly, this one will be D7. This one will be D6. So distance is nothing, but I'll take the data point. So xm minus xm bar. I hope you guys remember, if I put a bar on a variable, it becomes the average. So this is my average marks, which is 49. Average marks. So 27 minus 49, that will be my D1. 52 minus 49. 48 minus 49. 33 minus 49. 39 minus 49. 65 minus 49, and finally 82 minus 49. Now if I ask you what is the average distance, from the center, basically mean how much on an average a data point is deviated from the center. Now if I have to find out average, I have to take the sum of all these values, right? The problem is that few of the values are above the average, which would result in a positive value. Few of the values are below the average, which would result in a negative value. And if I simply take the sum of all these data points, the positive will cancel out negative. So we would get a very wrong value. And if I know that the center is 0 and we have some positive value, some negative value, then everything will be, you will get a value close to 0, which basically mean there is no variation, which is wrong, right? In order to overcome this problem, I will take distance square. I will convert the positive error or the negative error into the square, so that the positive and negative can be nullified. We can get rid of these positive signs and the negative sign. So let me just quickly write down what we are left with. So this will result in, I'll just quickly write down all the numbers because I have already calculated it. Now here you can see that I'm having minus 16 and plus 16, and if I simply take the sum over all the d, this minus 16 will cancel out plus 16, so I will not get the contribution of these two numbers. Similarly, you can see that I'm having minus 22 plus 33, minus 1 plus 3. So we are having some values which are positive, some values which are negative, and we cannot simply take the sum. So we will take distance square. So 22 to the whole square is, I have already done it, so 484, 9, 1, 256, 100, again 256 and 1089. Now we will take the average of the distance square. So what we have to take? Average of distance square. Now you guys can ask me that, Sumit, why you have taken a square, why you haven't taken the absolute value? So I would have simply taken minus 22 as just 22 and minus 16 as just 16. Now please remember that when we are working with statistics, we are using a lot of calculus also, and as of now I cannot show you where I would be working with calculus, but as we proceed forward, you would see that statistics is heavily dependent on calculus. And when we talk about functions, the function or the derivative of a constant is always 0, and derivative of a square term, which is d square, or maybe a derivative of a function which comes with a polynomial value, can be differentiated. So your calculus does not works with constant, does not works with functions which are constant, and that is the reason we will not be using those, we will not be using the absolute term, and we will be using the square term. So we have to take the average of d square, and you already know the formula, which is summation over d square and divided by n. So if I take the sum of all the observations which are present in the column d square divided by 7, I would get the average distance, or not just the average distance, I would get the average of d square. So this would be 2195 divided by 7, which is 313.57. Now this value is known as variance, which is 313.57. The problem with variance is that you can practically not make sense out of it. I'm not able to understand what this value means. And if you remember, it was d square. D square is equal to 313.57. Variance is also known as sigma square. It is known as sigma square. This is a Greek letter, sigma square. So my sigma will be square root of 313.57, and this would get us 17.65. This is my sigma. Now what is the meaning of this? Now sigma square is my variance. Variance is basically my sigma square, while sigma is my standard deviation. Standard deviation is my sigma. So standard deviation talks about the average distance that the data points are deviated from the center. So on an average, the data points are 17.76 marks above or below the mean, and that is what this standard deviation means. How much on an average the data points are deviated from the center, and that is 17.65. Now if this value is very low, which basically means the values are closely concentrated around the center point. For example, if I go back for this subject B, this one, you will get the value of sigma, which is my standard deviation, to be high, while for for A, which is this case, I would get the value of sigma, which is standard deviation, to be low. So if I call this as sigma A and sigma B, then my sigma A would be less than sigma B. The standard deviation in subject A would be less than standard deviation in subject B. When I say the standard deviation is less, that basically means all the observation or most of the observations are scattered very close to the mean. While when I say standard deviation is high, that basically means most of the observations are scattered far away from the mean. Now this gives you a better idea regarding how your data looks like. If you guys want to practice, you can see that we have already calculated the mean, median and mode of the age variable. We were having 13 students and their respective age. We have already calculated mean, median and mode. Now for practice, what you guys can do, you can quickly calculate the standard deviation of this particular data, and then you can try to understand it. So if you have to explain to the principal or to any person about how this class looks like, so we have already seen one segment that this class is having the median to be 26, which basically mean 50% people or 50% students fall below the age 26 and 50% fall above the age 26. Now if you get the standard deviation of, let's say, 5 years, I'm just throwing a value, I have not calculated it, so I'm just giving you this task to calculate this. But let's say if the standard deviation of this data is 5 years, then that basically means on an average the students are having 5 years above the central point, which is 26. So let me just quickly draw it. So let's say this is my student ID, this is my age, this is my center, which is 26, and if I'm having a standard deviation of 5 years, that basically means I'm having few students who are above the age, above the middle age by 5 years. So 26 plus 5 will give you 31, right? And 26 minus 5 will give you 21. So you can see that you can say that most of the students in your data are between 21 to 31, right? So using the measures of measures of central tendency, we get the central point. Using the measures of variation, we get how the data is scattered around the central point. But there is a problem. The problem is, let's say, if I'm having two subjects, let's say I'm having a subject maths, having a standard deviation of, let's say, 15 marks. And then I'm having age, having a standard deviation of, or maybe let's say I'm having another subject science, having a standard deviation of, let's say, 20. Now can I compare these two standard deviation? Can I say this is high and this is low? Well, we cannot do that. Using standard deviation, we cannot compare the variations among the series. Now please remember, this is a very important note, that standard deviation talks about the variation in the individual series. And we cannot use it to compare the variation among the series. So how we can compare the variation among the series? For this we have the next measure, which is coefficient of variation. So now let's try to understand coefficient of variation. Coefficient of variation. As I've told you, standard deviation is limited to describe the variation within that series. So if I'm saying that the standard deviation of the maths marks is 15 and the standard deviation of science marks is 20, I cannot use these two individual standard deviations to compare the variation among the series. For that we have a different metric known as coefficient of variation. Let's take one example. Let's take two series. Series X, which is having 1, 2 and 3 data points. Series Y, which is having again 3 data points, 101, 102, 103. Now if I take the average of X, which it will came out to be 2, average of Y will came out to be 102. Similarly, standard deviation of X will be 0.81, standard deviation of Y will be 0.81. Now, both X and Y are having the same standard deviation. Can I say that they have the same standard deviation, or can I say that they are having the same variation? If you closely observe, you will find out that this is not true. While in the series X, you can see that the third element, which is 3, is 3 times of the first. While in series Y, I cannot say the third element is 3 times of the first. Right? So they both are not having same variation. X and Y are not having same variation. How we can compare the variation? How I can say that X is having more variation, Y is having less variation? Because standard deviation is getting us the same value, 0.81, 0.81. How we can get, or how we can compare? For this we have coefficient of variation, which is nothing but the ratio between the standard deviation to the mean of the data. The standard deviation to the mean X bar. For coefficient of variation for series X would be 0.81 divided by 2. For y, it would be 0.81 divided by 102. So this would be 0.405 and this would be 0.007. Now if we closely look into these two values, which is 405, so 0.405 and 0.007, this particular series, which is series X, is having the coefficient of variation of 0.405, while series Y is having the coefficient of variation of 0.007. And I have already told you that the series X is having more variation than series Y, because in this series the third element is 3 times the first, while I cannot say the same thing for series Y, right? So when we have to compare two series, or we have to compare the variation among two or more series, we look at the coefficient of variation. A higher value represents higher variation. So this series is having higher variation when compared with series Y. So using coefficient of variation, we can simply compare the variation among the series, and we should not be using standard deviation. I hope this makes sense. Now here you can see I have taken one simple example, and here we'll be using all the measures, which is measures of central tendency and measures of variation, to understand how these three products are performing in terms of sale. And please remember, this is the number of units. So for product number 1, in month 1, 929 units were sold. Similarly, for product 2, in month 1, 1240 units were sold, and so on. So we can quickly find out the average, median, and mode for each of them. So is equal to average of this particular column, and I can simply extend this formula to all other cells. Similarly, median will be is equal to median. I want median of all these cells, and I can simply extend this to all other cells, and then we have mode, so is equal to mode. Now here if you carefully observe, I do not have any mode, so my mode is not available, and I have told you previously. So if I do not have any observation which is duplicated, which is repeated for more than one time, which is having the highest frequency in our data, we will not be having a mode. So we only have average and median. So I'll simply delete this because we don't have a mode. So let me delete this. Now if you compare the average and the median, you can see that for the sales of product number 2, the average and the median is quite close to each other, while the same thing can be viewed for product number 3. But there is a difference. There is a vast difference. I would not say vast, but there is quite a good difference in the average and the median for product number 1. Let's try to look at the measures of variation also. So we will calculate the standard deviation. So is equal to STDEV, and we will use this STDEV, this one, standard deviation. And I can just simply extend this And now we will calculate the coefficient of variation, COV. So this is given as the standard deviation divided by its average. Now these are the numbers which we have to carefully read and make sense out of them. What we can conclude about these three products? Let's try to understand them. Now if you carefully observe, and I would start with product number 2 first. In product number 2, you can see that the standard deviation is very small, while the coefficient of variation is also very small. Here also you can see that coefficient of variation is 0.23, here it is 0.22, but here it is 0.04, which basically mean among all these three series, the lowest variation is with the sales of product number 2. Also, if you look carefully, the median and the average is very close to each other. Also, the average is highest among all the three products. So what I can conclude about product number 2? Number 1, the product number 2 is very stable in the market because it is not having variations. In month number 1, same sale. In month number 2, approximately same sale. Month 3, same sales, and so on. Also, it is always consistently high, and that is the reason that average is the highest at 1262.5 units. For product number 3, a similar behavior can be seen, but on the lower side. The average is 556, which basically means when compared with product number 1, product number 2, and product number 3, when compared with product number 1 and 2, the sales of product number 3 is on the lower side or the lowest side. While the coefficient of variation for this, which is product 3 and product 1, is approximately the same, which basically means they both are varying at the same rate. The variation is approximately the same. So you can assume that one, which is product number 3, is on the lower side and it is varying around that. Product number 1 is on maybe second lowest and varying around that, and product number 2 is on the highest. So if I just color code them, I would say product number 3 would be coded as red. Product 1 I can put it as yellow, and 2 I can put it as green. And the reason I'm putting it as green because it is the most stable product in the market, while sales of product number 3 is on the lower side. That's the reason we have assigned a red color, and product number 1 is having the sales between the highest and the lowest sale, which is product 2 and product 3. So we have assigned a yellow color. Now you can see that using these measures, we can better make conclusions about the data. We can better explain the data, and that is the power of descriptive statistics. So you have seen that in this particular descriptive statistics segment, we have talked about how we can explain the data. We have talked about the various types of variables. We have talked about qualitative, quantitative, right? Then we started our discussion around what are the various measures of central tendency. We talked about mean, median, mode. Then we compared all of them. Then we talked about measures of variation, where we looked into range, variance, standard deviation, coefficient of variation. And finally, we have concluded all our learning into this table, where we have compared the sales of these three products to conclude about which product is better and which product is not good. Now, this is what the application of descriptive statistics is. There is one small topic which is very related to outliers. I'll just quickly explain you that. Though that is not so much common in the descriptive world, but quite important to understand. I have told you about outliers, right? Over here. So I have told you that in this particular series, where we have the age, 32 is considered as outlier. And what is outlier? Outlier is that observation which is very different from majority of the data. Now there is one particular topic which is known as the leveraging point or leveraging data point. What is that? Let's take one very small example. So let's say I have this data and this is the stock price. So here we have the day of the month and here we have the stock price of a particular stock. Let's say on day 1 the stock price was somewhere around here, then over here, then over here, then here, then here, and one day it jumped over here, then came back to its normal position like this. Now at the very first, like if I provide you with this data, all of you will say that this is outlier. This is particularly the outlier data point, which is true, this is outlier. But as soon as I provide you one additional information, your answer will change. Now if I tell you that on this particular day, let's say this is day number 15th, or maybe let's say day number 25. So in the 25th day of month, let's say March 2023, let's say the stock market or the stock exchange, or let's not talk about stock exchange, let's say this company, let's say this is the stock price of the company Reliance. So on 25th day of March 2023, Reliance announced a major product, or they made they basically conducted a conference. They conducted a meetup in which they announced a major change in their policy or major change in their product, due to which the stock price suddenly raised to this particular point. Now this is not an outlier, this is the leverage data point, because it has been leveraged due to this event. So I cannot say this is an outlier, this is a leverage data point. So there is a difference between outlier and leverage data point. If I go to this particular example of age, I cannot say this is leverage data point, because this person has not, or the age of this person has not been impacted by any external factor. So I cannot say this is an leverage data point. This is just an outlier. But in this case, where we are considering the sales of a particular stock price of a particular stock, let's say Reliance, this data point is the leverage data point because it has been influenced. The jump is because of a particular external factor, which is nothing but the announcement, right? So I hope you guys are clear till this point. Now we will move forward to the next particular discussion, which is probability. So now let's start with the topic probability. Now we started with descriptive statistics. We have to talk about inferential and hypothesis. But before we can move forward to understand inferential and hypothesis, we have to first of all understand what is probability. You guys must have learned about it in your 10th standards or maybe in your college days. But today we will try to understand the most important topics within probability, which will help you to understand inferential and hypothesis. So let's start understanding probability. Now, the term probability, most of you are familiar with this. So before we talk about probability, we have to understand what is a random experiment. Random experiment. Random experiment is a particular experiment in which you are not certain about the outcome. For example, if I toss a coin, I am not certain if I will be getting a head or a tail, right? If you are certain about it, then we don't need probability, right? So let's say if I already know that the coin is going to land as head, then I don't need probability, because probability is all about finding out what is the chances of getting a particular event, right? So what is a random experiment? It is something, or it is basically an experiment or an event for which I am not sure about the outcome. I am not certain about the outcome. So let me just quickly note it down. It is basically an event for which I am not certain about the outcome. For example, roll of a dice. Roll of a dice. Now, if I roll a dice, I know that I may get 1. So either 1, 2, 3, 4, 5 or 6. But am I certain that I will be getting a 1? No. Am I certain that I'll be getting a 2? No. I may get any of the outcome within 1, 2, 3, 4, 5, 6. So rolling a die is particularly a random experiment because I am not certain about what is going to be my outcome. Similarly, let's say about my birthday. So now you are not certain about what is my birth date, but there is a difference. If I talk about my mother, she is very much certain about what is my birth date. So for my mother, my birth date is not a random experiment. But for all of you listening, my birth date is a random experiment because it can be anything. It can be any year, it can be any month, it can be any day. So sometimes a random experiment or the uncertainty is maybe because of the lack of information. For example, my birth date. If you know about me, if you are my friend, then you might be very much certain that my birth date is in this year, this month, and this date. So there is a difference between a random experiment for which you are uncertain about the outcome and some event for which you are certain, like my birth date. So that is not a random experiment for my mother, but for all of you, it is a random experiment. So I'm just taking example of all the random experiments, roll of a dice or maybe toss of a coin, and we can note down all such random experiments. Now, what is a sample space? As I was talking about, that when you roll a die, you may get any of the outcome within 1 to 6, right? So 1, 2, 3, 4, 5, 6, you can get anything. The set of all the possible outcomes out of an experiment is known as the sample space. So what is the sample space? The set with all the possible outcomes out of an experiment. So if I take the example of roll of a dice, I may get 1, 2, 3, 4, 5 or 6. So this is my sample space for rolling a dice. For toss of a coin, now if the coin is a fair coin, which basically means
one side will be head and one side will be tail. So I may get either a head or a tail. Now this is basically my sample space for the random experiment toss of a coin. If I talk about my birth date, in that case, all the years, maybe let me just limit the sample space to 1996. So if you know that the birth year is 1996, then in that case, the sample space will be all the months, and within each month, all the dates or all the days. So your sample space will have quite a good number of outcomes, right? So this is what my sample space is. Now what is probability? So probability of a particular event X is basically how many times that event has occurred in your sample space. So number of times the event occurred in the sample space, and we divide this by the total size of the sample space. Total number of outcomes, so total number of outcomes in my sample space. Now please remember one thing. If I go with the definition, this is the very accurate definition, that the number of times a particular event has occurred divided by the total number of or total size of the sample space. But there might or there may be various ways of writing a sample space. Let's try to quickly understand the difference, because this is the major mistake most of the students commit while calculating probability. So this particular sample space is having all the outcomes which are equally likely. So all the outcomes in this sample space are equally likely. What is the meaning of equally likely? So if you already know about it, you can just pause the video and comment on this particular video. But equally likely basically mean that if I choose any of the event, it will have the equal chance of occurrence. For example, what is the probability that I will get the number 1 if I roll a die? It is simply 1 divided by 6. What is the probability that I'll get 2? Again 1 divided by 6. 3, 1 divided by 6. 4, 1 divided by 6. 5, 1 divided by 6. 6, 1 divided by 6. So all the events in this particular sample space are equally likely because each of them are having the probability equal to 1 by 6. Similarly, if I take this sample space is also equally likely. So what is the probability of getting head? 1 by 2. What is the probability of getting tail? Again 1 by 2. So the probability of getting head and tail are equally likely. But now let's take an example where I am tossing 2 coins. So I am having 2 coins. My drawing is really good, so I'll use my skill over here. So let's say these are my 2 coins. Now what are the possible outcomes? I might get a head, a head tail, a tail head, or a tail tail, right? Now what is the probability that I'll get a head and a head? Like both coins land with the face head and head. This is 1 divided by 4 because here I'm having total 4 outcomes and the probability of getting headed is only one event is there. So the probability of getting headed is 1 by 4. This is 1 by 4. This is 1 by 4. This is 1 by 4. So this sample space is also equally likely. Can I write this sample space in another way? Yes, we can. So let's say now my sample space is the number of heads. So I can have 0 heads, 1 head or 2 head. This is also a sample space, but there is a difference. This sample space is not equally likely. This sample space is not equally likely. So the probability of getting 0 head is 1 by 4. And please remember here each number represents the number of heads. So the probability of getting 0 head is 1 by 4. Probability of getting 1 head is this plus this. So it can be either head tail or tail head. So 1 by 4 plus 1 by 4, it is 1 by 2. And probability of getting 2 head is again 1 by 4. So here you can see that the probability of each event is not equally likely. So whenever you are calculating probability, you have to make sure that your sample space should be equally likely. If it is not, then you have to carefully calculate your probability. I hope this is making sense. So now let's talk about some of the rules of probability. So I hope every one of you are clear with the idea of random experiment and the sample space. There is one particular term which is known as event. Now what is an event? Any possible outcome or group of outcome out of a random experiment or out of a sample space is known as an event. For example, if my experiment is toss of a coin, then I may get a head or a tail. So out of this experiment, getting a head is an event, getting a tail is an event. Similarly, if I am tossing 2 coins, I may get head head, head tail, tail head and tail tail. In this case, getting 2 heads is an event, getting 1 head is an event, getting no head is an event. So all of these are my events. So event is nothing but a particular outcome or group of outcomes out of a sample space. So outcome or group of outcomes out of a sample space. This is my event. So what all we have talked about? Number 1, random experiment. Number 2 is sample space. And the 2 ways in which we can write the sample space. One is equally likely sample space. Other one is not equally likely. The third topic which we talked about was event. Now let's talk about the rules of probability. So when you are using probability as a measure or as a tool to basically calculate the possibility or probability of a particular event, there are some rules which we have to keep in mind. So let's talk about them. They are also known as the axioms of probability. I'll just simply write it as rules of probability. So rules of probability. Okay, the very first rule is, given a sample space, the probability of each outcome will always result to 1. The total probability is always equal to 1. Let's try to understand it. Let's say I'm given with a sample or sample space of roll of a dice. So when I roll a dice, I may get 1, 2, 3, 4, 5 or a 6. We know that the probability of 1 is 1 by 6. So what is the probability of getting 1 in the dice is 1 by 6. What is the probability of getting 2? It's again 1 by 6. Probability of 3, again 1 by 6. And this is equal to probability of 4, probability of 5 and probability of 6. All is 1 by 6. Now if I take the sum, probability of 1 plus 2 plus 3 plus 4 plus 5 plus 6. If you do the quick math, you will find out that it is equal to 1. That is my first rule. So summation of pi, where I is running from 1 to n, or I is over my sample space. So I'll just simply write where I belongs to my sample space, the sum of all the probability is always equal to 1. This is my first rule. Let's talk about, so let me just formally write it down so that you guys are having all these notes, and whenever you prepare for your interview, if you just read all the note, it will be very easy for you to pass your statistics round. So the sum of all probability over the sample space is always equals to 1. This is my first rule. Now let's understand the second rule, which is known as the rule of sum or addition probability. It says that the probability of A union B is equal to probability of A plus probability of B if A and B are disjoint event. So there is a condition: if A and B are disjoint. Now don't need to worry, I am not talking anything in German. This is very simple to understand. Let's take one simple example. Let's say I'm tossing 2 coins. So when you toss 2 coins, you may get 2 heads, 2 tail, 1 head, 1 tail, and 1 tail, 1 head. Now if I ask you, what is the event of getting 2 head, or so let's take, what is the event of getting 2 different outcomes? So let me write it down. What is the event of getting both coins with different outcome, which basically mean both coins land into a different outcome. So one is head, so another one will be tail. If one is tail, another one will be head. And we already know that there are only 2 possibilities. So my event would be head tail or tail head, right? Let's call this event as event A. Now we have another event where both coins lands into same outcome, which basically means if coin 1 is head, coin 2 is also head. If coin 1 is tail, coin 2 is also tail. So this is same outcome. So both coins with same outcome, and that would be head head, tail tail, and this is my event B. Now if I take the union means addition. If I take the addition of these two sets, then according to the rule, it is the sum of individual probability of the event. So what is the probability of event A? If you guys have understood, you can simply answer this, and you can add your answers in the comment section. So the probability of A is, there are 2 outcomes with which matches my condition. So head tail and tail head. There are total of 4 outcomes in my sample space. So the probability is 2 divided by 4, which is simply 1 divided by 2. Similarly, probability of B is also 2 divided by 4, which is 1 divided by 2. Now if I take the sum, or if I take the union of these 2 events, so what is the union of A union B? A union B means I will combine all the events in my sample space. Now since we do not have any common element, my union would simply be head tail, tail head, head head, and tail tail. And if I ask you what is the probability of A union B, you will just simply say it is 4 divided by 4, which is 1. Now if I add these two probability of A plus probability of B, you can simply add 1 by 2 plus 1 by 2. This is also 1, right? So that basically means if 2 events are disjoint, so here you can see event A and event B are disjoint. Why I am calling them as disjoint? Because they do not have any common event. You can see that in event A I am having head tail, in event B I am having head head tail tail. There is no common event. So when two events A and B are disjoint, they do not have any common event, then the probability of the union is always equal to the individual sum of probability, and this is what we were trying to prove. So let me just quickly highlight this, and this is my second rule of probability. This was my first rule. This is my second rule, and this rule is only applicable when your two events are disjoint, where we have taken this example, A and B are disjoint because it does not have any common event among them, right? Simple. Now let's understand the third rule. And third rule is also very much closely associated with the second rule, where we proved that probability of A union B is always equal to the probability of A plus probability of B if A and B are disjoint, right? Now, there is one more rule. If they are not disjoint, then probability of A union B is probability of A plus probability of B minus probability of A intersection B. Again, you guys would be thinking that it is something German, but not. Let's try to understand it. In order to understand it in a better way, we will take the example of playing cards. Playing cards. And I hope most of you would be aware about the playing cards. But if you are not, don't need to worry. Let's try to write down the complete details about how many playing cards we have, what are the various suits and everything. So in total, a playing card or a deck of playing card comes with 52 cards with 4 suits. So we have club, spade, heart and diamond. Now if you guys are aware about it, then you can easily point it out that club and spade, these are two black cards, while heart and diamond, these are my red cards. So club and spade are my black cards. Now club is having 13 cards, spade is having 13, heart 13 and diamond 13. So each of them is having 13 cards. Now which all 13? So let's write down the complete structure. So each suit comes with total of 13 card, which starts with ace, a card of ace, then 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 3 cards which are known as the jack, queen and king. Now this is the complete portfolio of your playing cards or the deck of a playing cards. Now let's try to calculate some probability of some events. So what is the probability of getting a jack? What is the probability of getting a card which is a jack card? Now we already know that a jack or card of a jack can come from any of the suit. So I may have a jack from club, so I'll write CJ, club of jack or jack of club, you can say anything. Then we have a spade. I can get a jack from spade. I can get a jack from heart. I can get a jack from diamond, right? These are the total 4 outcomes or total 4 favorable outcomes, while the total number of outcomes or total number of events in my sample space is 52, because each card is a outcome, right? So the probability of getting a jack is 4 divided by 52, right? What is the probability of getting a black card? Now we already know that club and spade, or let's simplify the question so that I can demonstrate you the rule that we are trying to prove. So what is the probability of getting a heart? Now we know that there are total of 13 hearts. Total of 13 hearts, because heart itself is a suit. So we have 13 cards belong to heart and total are 52. So the probability of getting heart is 13 divided by 52. What is the probability of getting jack and heart? Now before we jump to the answer, I know most of you would have already calculated the answers. Let's try to note down all the outcomes which matches this condition, and then it will be easy for us to understand if we are going in the right direction or not. Jack and heart, which basically means the card need to be a jack card and the card should be a heart. Now if you closely try to understand this problem, you will find out that it is only one card that can satisfy these two conditions. A card which is jack plus it also belongs to a heart. So the probability is 1 divided by 52, because I will have only one card which is heart of jack or jack of heart. Now what is the probability of jack or heart? Now or means nothing but the addition. Before we calculate this probability, let's write down all the outcomes or all the events. So it will be heart of ace, heart of 1, heart of 2, heart of 3, 4, 5, 6, 7, 8, 9, 10. Then heart of jack, heart of queen, and heart of king. These are all my heart. These are all the cards that belong to the suit heart. Now let's write down all the jack cards. So I can have a jack from heart, so HJ. I can have a jack from club, so CJ. I can have a jack from spade, so SJ, and then DJ. Now if I combine them, if I take the union of them, so let's call this as event B, this as event A. If I take A union B means I have to create a set which is having all the events from A and all the events from B. But if there is an event which is replicating for 2 times, I have to only pick one of them, right? So if I combine them, you will find out that there is one event which is common in these two sets, and this is this card. Let me just quickly circle it. So heart of jack, this card is available in both these sets, right? And if I have to combine these two sets, I have to count this particular card only for one time. So if I write down all the combined event, it will be from heart of ace, heart of 1, heart of 2, heart of 3, 4, 5, 6, 7, 8, 9, 10. Then heart of jack. Now I have counted it already for one time. Then heart of queen, heart of king, and then I will write down these 3 cards, which is CJ, SJ, and DJ. Now how many events I am having in this? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. The mistake is this is not H1, this is H2. So after ace, it starts from 2. So I should not be writing this. In that case, my outcome will be 16 divided by 52. Probability of jack or heart is simply 16 divided by 52. Now if I go with the formula, what is the probability of getting heart? It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is by 13 divided by 52. This is 4 divided by 52, right? if I add them without subtracting this common event, I will be basically counting this card for 2 times, which is wrong, right? If I have to add these two set, I have to make sure that I'm just counting this card for 1 time, because logically I have only 1 card, right? So that is the reason when I'm combining them, I will write probability of A plus probability of B minus the common card or common event which occurs in these two sets. So A and B. Now if A and B is 0, A and B can only be 0 when the two sets are disjoint. I will go back to my rule number 2. So if A and B are disjoint, probability of A intersection B is 0. When A and B are joint, basically mean they have a common event, then my probability of A or B, A union B, is equal to probability of A, which is 13 by 52 plus 4 by 52 minus 1 by 52, because I am having 1 card which is common and I have calculated it over here. So this will be total of 17 minus 1, which is 16 divided by 52, which is my third rule of probability. I hope every one of you are clear with this. This is my third rule. Now let's look at the one final rule, which says probability of A plus probability of A complement is always equal to 1. Let's try to understand that. Now the fourth rule and the final rule is probability of A plus probability of A complement is equal to 1. What is the meaning of this? We have already seen this, but let's try to understand it again. Let's take an event, or let's take a experiment, the random experiment, where I'm tossing 2 coins. So toss of 2 coins, and I hope all of you are able to now build the sample space, which is we will get 2 heads, 1 head, 1 tail, 1 tail, 1 head, 1 tail and 1 head, and then 2 tails. This is my sample space, and this is a equally likely sample space, right? Because each event is having same probability, right? Okay. Now, if I ask you, so let's say event A represents both coins lands up with same outcome. Both coin lands up with the same outcome. What is the complement of this? What is the meaning of complement? The opposite of this statement. So I'm saying both coin lands up with same outcome. So the opposite of this is both coins did not or does not lands up in the same outcome. So let's write the complement. Both coins does not lands up with the same outcome. Now what is going to be the event for A? It will be H and tail. The complement of this will be H tail, head tail and tail head. Now if I add these two probabilities, so probability of A is 1 by 2, probability of A complement is also 1 by 2. So probability of A plus probability of A complement is also equal to 1. This is a very important rule, because sometimes you need to calculate the probability of a sample space and you just know one event. Then it is simply, you can use this probability rule and you will be able to land up in the probability that you are looking for. I hope all of you are now clear with all the 4 rules of probability, which is the addition of or the sum of all the probability over the sample space is always equal to 1. Second one is probability of A union B is equal to probability of A plus probability of B if A and B are disjoint. If they are not disjoint, then you have to subtract the probability of A intersection B. And final one is probability of A plus probability of A complement is always equal to 1. Now let's try to understand the various types of events. A particular event or two events can be dependent or independent. These two terms might be familiar with you, but now let's try to understand them with an example. So now let's try to understand what is particularly dependent events and independent events. Dependent. First, we will try to understand the dependent events. When I'm saying events, I'm basically talking about two events or two or more events, right? So let's take two events. I'm tossing a coin. So again, my drawing skills. So this is, let's say this is a coin and this is a fair coin. Fair coin. Now, if I toss this coin for 2 times, so my experiment is to toss the coin for 2 times. Now when I toss it for the first time, so this is my first toss. When I toss it for the first time and let's say heads appeared. So let me write it down. When I tossed it for the first time and heads appeared. So we know that when I toss the coin and it lands up into head, you know this. So let me write that the outcome of the first toss is head. Now when I'm tossing the same coin for the second time, so second toss. Now remember the coin is same. I'm having the same coin but I'm tossing it for a second time. Now when I toss it for second time, is it more likely that I would get a tail because the first one was head? So my question to all of you is it more likely that we would get a tail since the first outcome was a head? Now all of you would say no. Why? Because the next outcome can again be having the probability of getting head and tail to be equally likely, which basically means if I'm tossing it for first time, I may either get a head or a tail. And what is the probability of getting head and tail? 0.5, 0.5, which is 1 by 2, 1 by 2. If I toss the same coin for the second time, again the probability of getting head and tail is 1 by 2, 1 by 2, which is 0.5, 0.5. So what I'm trying to say is, if I toss the coin for first time and if I toss the coin for second time, these two tosses are independent of each other. The probability in the second toss is not getting influenced with the outcome of the first toss. If my outcome in the first toss is head, in the second toss it is not influencing, right? In the second toss it can be still be head or tail. So in simple words, first of all, the answer for this question is no. So I'll write a big no over here. And the rule is the outcome of the first event is not impacting the outcome or the probability, the outcome or the probability of the second event or the second toss, and hence they are independent events. Now there is a very good so in probability theory there is a topic known as gambler's fallacy. What gamblers think that if, so let's say if the game is of tossing a coin for 10 times. Now let's say there is a gambler who is given with the choice, who is given with the game to toss the coin for 10 times. For the first 5 times, let's say, he has got all tails. So tail, 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 tail and tail. So for the first 5 times, he has got all the tails. Now what gambler's fallacy is that he will think that for the next 5 times, he will get a head. So according to gambler's fallacy, the outcome for next 5 tosses should be head, 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 head and head. Why? Because according to the probability of head and tail, it should always be 0.5, 0.5. No, that's wrong. It is only true when you are tossing the coin for very large time. That's known as the law of large number. So this is known as gambler's fallacy. This is wrong. This is wrong. This is only true, this is only possible when you are tossing the coin for very large time. So if I keep tossing the coin, let's say for 10,000 times, you will find out that approximately for 5,000 times you obtained a head and 5,000 times you obtained a tail. But if you are tossing the coin for 2 times and you expect that I will definitely get head for first time and tail for second time, that is wrong. That is the gambler's fallacy. So I hope you guys will not be landing into the gambler's fallacy, and I hope you are clear with the dependent event. Independent event, independent. So when 2 events are independent, the probability of A and B is simply as probability of A multiplied by probability of B. So for example, probability of getting head in first toss and probability of getting head in second toss is simply can be written as probability of head in first toss multiplied by probability of head in second toss, and this will be equal to 1 by 2 multiplied by 1 by 2, which is 1 by 4. I hope you guys are clear. Let me just quickly show you one example of gambler's fallacy which proves that when you toss a coin for very large time, then only the probability of head and tail will be closely or approximately be equal to 0.5 and 0.5. Now here you can see there is a very cool website which is seeingtheory.brown.edu. This is an open source website. Now it shows these are the true probabilities. Basically mean the probability of head is 0.5, for tail it is 0.5. Now I can flip the coin. So if I flip the coin for the one time, you can see that for the first time I obtained a head. So my probability of getting head is 1 by 1. If I flip it for one more time, I obtained a tail. So 1 by 2, 1 by 2. If I flip it for one more time, I obtain a head. For one more time, again a head. For one more time, a tail. For one more time, a tail. For one more time, a head. Now if I do it for 100 times, I obtained out of 107 times, head came for 57 times, tail came for 50 times. Let me do it for one more 100 times. Now you can see that now the probability of tail is more than the probability of head. If I do it for 1000 times, so which basically means I have to hit this button for 8 more times. So 1, 2, 3, 4, 5, 6, 7 and 8. Now just look at this, for 0.49, 0.51, very close to 0.5 and 0.5, right? So this is the law of large number. If I perform the experiment for very large time, then my observed outcome or observed probability will be close to the true probability, which is 0.5 and 0.5. I hope this makes sense to all of you. So now let's talk about dependent events. So dependent events. Now for dependent events, we will take a very simple example. Let's say I'm having a bag, and this bag is having, let's say, two orange balls. So we have two orange balls, and let's say some white balls. So for white balls, I'll draw it like this: one white ball, two white ball, and three white balls. So total I'm having 5 balls in which there are 2 orange, 3 white. So let me write it down. 2 orange and 3 white. Okay. Now the experiment is, we take a ball out of the bag. So take a ball out of the bag. We have to note the color. So note down the color. And we put another ball, we take out another ball out of the bag. So take one more ball out of the bag. And then we note the color of that ball also. Note down the color. Now please carefully remember that this experiment is without replacement. So let me just quickly demonstrate this example. Let's say this is my bag, and this bag is having 2 orange balls and 3 white balls. Now what is the experiment? I have to take a ball out of the bag. So this is my orange ball, and I note down the color. So we will write orange and we keep it outside. Then we again take a ball out of the bag. This is a white ball. We will note down the color and we will keep the ball out of the bag. So this is what is my experiment. I hope everyone is clear. Now my question is, we have to calculate the probability that I get a orange. So O. So first ball happens to be orange, second ball happens to be white. So what is the probability that I will get first ball as orange and second ball as white? Now let's solve this problem step by step. When I am taking out the first ball, so this is my first ball. When I'm taking out the first ball, the bag is having 3 white and 2 orange, right? So initial is 3 white and 2 orange. Now what is the probability of getting a orange ball or an orange ball? Probability of getting an orange ball. This is simply be 2 divided by 5. Why? Because I have 2 orange ball and there are total of 5 balls. Now I have taken this ball out of the bag. So the bag is now, so I will take this ball out of the bag. This ball is out of the bag now. Now the bag is left with 1 orange and 3 white balls. 1, 2, 3. Now what is the probability that my second ball is a white ball? So probability of second ball is a white ball. But there is a condition given to us. So given that, so this symbol means given that the first ball was orange. So we know that first ball was orange. Then what is the probability that my second ball will be white? This will be 3 divided by 4. So because we have 3 white balls and total are 4 balls. Now if I ask you what is the probability of getting orange and a white. So what is the probability of first ball as orange and second ball as white? Now this will be simply as probability of first ball as orange multiplied by probability of second ball as white, given that first ball was orange. So this would be 2 divided by 5 into 3 divided by 4. So this will be 2 times. So this will be 3 divided by 10. This is my probability of getting first ball as orange, second ball as white. So this is 3 divided by 10. Now here, if you carefully understand the experiment, the probability of second ball is dependent on the outcome of the first trial. So here is a note. The probability of second ball is dependent on the probability or the outcome of the first toss or first trial, or first I would say first trial is a correct word. So this is what is my dependent event is. Dependent events. So when two events A and B are dependent on each other, if they are dependent, then the probability of A and B is given as probability of A multiplied by probability of B, given A has already happened. This is my probability of A and B. Now this is the dependent rule when two events are dependent on each other. I hope this experiment, this example makes sense to all of you. Let's take one quick example to understand the dependent case in a better way. Let's say I'm again having a bag. This bag is having 3 black, and I want all of you to take out pen and paper and try to solve this. Pause the video, try to understand the logic and solve it. So the question is, the bag is having 3 black and 2 red balls. What is the probability of getting red, red, which basically means probability of red in first draw and red in second draw? This is my question. Now let's try to logically solve it. I want all of you to pause the video and try to solve it by yourself. I hope you guys would have solved it already. So let's say initially the bag is having 2 reds and 3 black balls. 3 black balls. Now the probability of the first ball being red is 2 divided by 5, right? Now this ball is out of the bag now. So I have taken out the ball and I have kept it outside. So the bag is now left with 1 red and 3 black. So 1 red and 3 black. Now what is the probability of getting the second ball as red, given that I have already taken out the first ball as red, given that first ball taken out was red? Now this would come out to be 1 divided by 4, because I am left with 1 red ball and total balls are left are 4. So what is the probability of getting red, red, which basically means red in first trial and red in second? This will be probability of first ball as red multiplied by probability of second ball as red, given first ball taken out was red. So this would be 2 divided by 5 multiplied by 1 divided by 4. This is 1 divided by 10. I hope you guys were able to solve this question. Now let's talk about random variables. Now random variables is something that quantifies the outcome of an experiment. Something that quantifies the outcome of an experiment. Now let's try to understand it in a better way. So let's say I am tossing 2 coins. So my experiment is toss of 2 coins. Now the sample space for this would be 2 heads, head tail, tail head and tail tail. Now how I can quantify the outcome? What is the meaning of quantification? Converting the outcome into a number or mapping an outcome into a number. So let's say my random variable can be, so are we assigning the variable with a sign or alphabet x. So my x can be number of heads in a toss of 2 coins. In a toss of 2 coins. Now this is my random variable and this will map the outcome of the random process, which was toss of 2 coins, into numbers. I will get 2, 1 and 0. How? So if I write head head, head tail, tail head and tail tail. Now this corresponds to 2 heads. So the number of heads when you toss 2 coins can be 2 heads. This both quantifies to 1 because in both of these outcome I am getting 1 head and this is mapped to 0 because there is no head. So 2, 1, 0. This is my random variable x. Similarly, I can have a random variable y with number of tails in a toss of 2 coins. In a toss of 2 coins. So let's say y will also represents 2, 1, 0, right? I can have 2 tails, 1 tail or 0 tail. I can also have a random variable where I have taken a random number. For example, let's say I have stated that if you get, so there is a game, let's say there is a game which says if you get 2 heads, I will give you 10 rupees. So you win 10 rupees. You win 10 rupees. For any other outcome. For any other outcome, you have to give me 5 rupees. So you pay 5 rupees. Now in this case, let's say I'm interested in the amount I can win. So x is my random variable. X represents the amount or the total price. So the amount I can win, and it can either be 10 rupees. So I will write plus 10 because it is a gain for me. So plus 10 and minus 5 because minus 5 represents loss. So here what I have done, if my experiment is having these 4 outcomes, then this is mapped to plus 10 and all of them are mapped to minus 5. This is also a valid random variable. Now random variables are essentially divided into 2 categories. A random variable can either be a random variable, can either be discrete, or it can either be continuous. Now, what is discrete random variable, or what are the discrete random variables? Well, discrete random variables are those variables for which the outcome can be quantified into integers which are countable. For example, number of heads in a toss of 2 coins. I know it can be either 0, it can be either 1, it can be either 2. But if I ask you about you completing watching this video, so how much time you will take to watch this video? Now it can be anything from minus infinity to plus infinity. You can take 1 hour, you can take 1 hour 5 minutes, you can take 1 hour 5 minutes 50 seconds. There are endless possibilities, right? Let's take a simple example. Let me just go to a next page. For discrete, first of all, we'll take example. For discrete random variable, the outcome are mapped to integer numbers which are countable. We can simply count them. For example, number of heads in a toss of 2 coins. Or let's take one more example. Let's say there is a person who is trying to shoot a particular target. So this is my target. Here I am having the person, and this person is trying to shoot the target. So here is the target. Now let's say this person is trying for 10 times. So if the person try to shoot the target for 10 times, then what can be my random variable? My random variable can be the number of times the person hits the bullseye. So my random variable x can be number of times the person hits the bull's eye. Now, if you closely observe, this random variable can only take integer numbers. So I can only get, so the person can either hit the target or hit the bullseye for all the 10 times, maybe for 9 times, for 8 times, for 7, 6, 5, 4, 3, 2, 1 or 0. 0 means the person was not able to hit the target for any time. This is my discrete random variable. Can this variable take any value other than all these possibilities that I have written? Can the random variable x that you can see on your screen, can this variable take 1.7? No, it cannot take 1.7. Similarly, this random variable cannot take 10.5 or maybe 9.11. So it can only take these limited numbers. So this is why this is known as a discrete random variable. Let's talk about continuous random variable. Now, continuous random variable can take many values. The outcome are many possibilities. So for example, let's take first of all an example. The time an employee takes to commute from home to office. Now this is my random variable x. The time an employee takes to commute from home to office. Now this can be anything. Let's say we have defined a range. Minimum is the person minimum takes 10 minutes, maximum is let's say 1 hour, or let's say we will keep the scale in minutes itself. So we have written 10 minutes, so this is 10 minutes, and the maximum is 60 minutes. Now between these two minimum and maximum, between this range, I can have endless numbers, endless, right? There can not be a particular point that I can pinpoint. I cannot say the person would take 10 minutes, 5 seconds, 3 milliseconds, 2 nanoseconds. It can be endless possibilities, right? So this kind of random variable is known as the continuous random variable. So here x represents my continuous random variable. When I talk about discrete random variables, there are some properties and distributions associated with them. Similarly for continuous random variable. The reason we are talking about it is because we wanted to generalize them. I will talk more about them. I will talk more about how we can generate a distribution out of them. But before that, let's briefly talk about a very important topic known as expected value. And we will take this example to calculate the expected value. What is the expected value? So I'm just taking a topic out of the random variable to talk briefly about expected value. And then we will jump to distributions. So expected values. Now when we talk about expected values, it is basically the average value of the random variable. Average value of the random variable. Now let's say I'm taking one example. Let's say the number of heads. The number of heads in a toss of 2 coins. Now this is my random variable x, and this random variable can take 2, 1 and 0. So either I can get 2 heads, 1 head or 0 head, right? I have already shown you this. Please remember this. Now, what is the expected value of this random variable x? So what is the expected value of x? Expected value is nothing but given as summation of I over x pi into xi. I would write it formally as xi into p probability of x is equal to xi. What is the meaning of this? So what is the so let me just quickly create a table with the random variable x and the probability of x. So random variable x, probability of x is equal to xi. So the random variable can take value 2, 1 and 0. Now 2 can come out from this event head head. 1 is the event of head tail and tail head, and 0 is the event of tail tail. So the probability of getting 2 is 1 divided by 4. This is 2 divided by 4, which is eventually 1 divided by 2, and this is 1 divided by 4. These are the probabilities. So the expected value of x is nothing but the random variable multiplied by the probability of that random variable. So 2 multiplied by 1 divided by 4 plus 1 multiplied by 1 divided by 2 plus 0 multiplied by 1 divided by 4. So this will be 2 times. So I'll get 1 divided by 2 plus 1 divided by 2, and this will be 0. So the answer is 1. Expected value is 1. What is the meaning of this? This means on a long run, if I perform this experiment for a very long time, if I keep on performing this experiment, I'm tossing 2 coins again and again. On a long run, on an average, this experiment would result in one head. So on a long run, you will observe that you are getting one head. This is the mean of this random variable. If this is not making sense, let's take a example in a game format, and then you will be able to connect with it. Let's say now I am having the same experiment. The experiment is toss of two coins. Toss of two coins. I may either get head head, head tail, tail head, and tail tail. Now we are mapping, so my random variable x is now the amount I can win. The amount I can win. Let's say two people are playing some game, and the condition of this game is if the person tossing two coins, or if the person tossing a coin for 2 times gets both of them are head, the person wins 10 rupee. For any other combination, the person has to pay 5 rupees. So the random variable x is plus 10 or minus 5. Now I'll quickly create a table. This is my random variable xi. This is probability of x is equal to xi. So person can win 10 rupees, so plus 10. Person can lose 5 rupees, so minus 5. What is the probability of winning 10 rupees? You can see the probability of winning 10 rupees plus 10 can only come when the person has obtained both head, which is 1 divided by 4, right? Probability of losing 5 rupees is getting either of the event, which is head tail, tail head, and tail tail. So head tail, tail head, and tail tail, and this is 3 divided by 4. Now I'll calculate the expected value of x, which is 10 1 divided by 4 plus minus 5 into 3 divided by 4. Now this will be 2 times 2, 2 times 5. So this will be 5 divided by 2 minus 15 divided by 4. Or for easy calculation, let's keep them, let's not cancel out the 4 because the numerator is denominator is both 4. So I'll get 10 divided by 4 minus 15 divided by 4. This would be denominator is 4. 10 minus 15 is minus 5 by 4. So minus 5 divided by 4, which is minus 1.25. Now what is the meaning of this value? This value basically means on a long run, if you play this game for very long time with your friend, on a long run, on an average, you would end up losing 1.25 rupees per game. So this is a loss for you. What was my random variable? The amount I can win. The random variable ends up in a negative value, which is minus 1.25. So on a long run, if you perform this experiment for a very long time and you play this game with your friend, then you will end up losing 1.25 rupees per game. And that is what you should do. So when you're playing a game, please make sure the expected value should always turn out positive for you. And you would have heard about this term, the house always wins. The house always wins, which basically mean in gambling, whenever you go to any casino or any gambling house, they always win on the long run. So if so many people are playing the same game, some of them will win while most of them will lose. So on a long run, it is a profit for the gambling house or for the casino. So some of them may win, some of them may lose. But on a long run, when many people are playing the game in the casino, the house will always win because their expected value is positive for them and negative for you. And all the games are made in such a way that the expected value is favorable to them. So now let's talk about distributions. What is distribution? So when we have a random variable, I hope you already know a random variable can be of two types, either discrete or continuous. So let's say I'm having a discrete random variable. And first of all, we are talking about the distributions for discrete. I will take an example for both and then we will talk in details about the variety of distributions we have. Distributions are very important and please listen to this topic very carefully. So when we talk about discrete random variable, we know that the outcome can be discrete, it can be integer, right? So let's take one example. Let's take one experiment of toss of two coins. And I have taken this experiment for so many times. So you already know that the outcome can be head head, head tail, tail head and tail tail, right? The random variable can be x can represents the number of heads and it can be 2 head, 1 head or 0 head. Now if I plot this distribution, so I am having a plot. In the x-axis I'm having the random variable and I already know this random variable can either take 2, 1 or 0. Here I'm having the count. So assume that you are performing this experiment of tossing two coins for many times and you have noted down the number of times you obtained 2 heads, the number of times you obtained 1 head, the number of times you obtained, let's say, no head. So let's say I'm creating a table and let's say so this is my trial number 1. So I'll write 1 over here. In the trial number 1, you obtained head, head. So here I will write 2. In trial number 2, you obtained head tail, so 1. In trial number 3, you obtained tail head, so again 1. In trial number 4, you obtained tail tail, so again 0. In trial number 5, you obtained tail head, so 1. Trial number 6, you obtained tail head, again 1. 7, you obtained head tail, so 1. 8, you obtain head head, so 2. Then 9, you obtain tail tail, so 0. And 10, you obtain tail head, so again 1. Now this is my outcome or random variable x. Now I will just count and create a plot. So how many times I have obtained 2 heads? So 1 time, 2 time. So I'll assume that this is 1, this is 2, this is 3 and so on. So for 2 times I obtained head, head. So I'll create a bar over here. Then how many times I obtained 1 head? So 1 time, 2 time, 3 time, 4 time, 5 time, 6 time. So 6 time, let's say it represents like this. And then how many times I obtained no head? So 1, 0 and 0, so 2 times. This is known as the distribution of discrete random variable, and we have a very good name for this distribution known as the PMF. This is PMF. This is known as the probability mass function. This is the probability mass function. Now, please remember this, that if I'm tossing one coin, so let's say if I'm just tossing one coin and we have already created this probability mass function. I hope you remember. I have shown you one website, seeingtheory.edu. In that website, you have seen that for the true probability, so the true probability of getting head and tail when you toss one coin is half and half, 1 divided by 2 and 1 divided by 2. So the probability of mass function of the true probability when you toss one coin will be 0.5, 0.5. So this is head, this is tail, 0.5, 0.5. But when you actually perform the experiment, this can change. This can be anything. This can be, let's say I'm having more head and less tail. So let's say this is 0.7, this is 0.3. When you tossed one coin for 10 times. So 7 times you obtain head, 3 times you obtain tail. Quite possible, right? This is known as the observed. This is known as observed. This is known as true. Similarly, for this example, the true, so what is the probability of getting 2 heads? It is 1 by 4. Probability of getting 1 head, it is 1 by 2. Probability of getting 0 head, it is 1 by 4. How? Because I have mapped them. Please remember, this probability is 1 by 4. Probability of 1 head will be 1 by 4 plus 1 by 4, which is 1 by 2. And this will be again 1 by 4. So the true PMF for this would look something like this, where this would be 1 by 4, which is 0.25, 0.5, and again 0.25. This is the probability PMF for my random variable x, which is a true probability. This is the PMF. This is for the discrete random variable. Now let's talk about the continuous random variable and how the distribution looks like. For continuous random variable, if you guys carefully try to understand the continuous random variable, we cannot have the discrete type values or integer values, but we can have range also. We can have range, right? For example, let's say the random variable is time an employee takes to commute between home and office. Now let's say we have defined the minimum and the maximum range. Let's say minimum the person takes 10 minutes, maximum the person takes 60 minutes. Now I can have endless possibilities between these two numbers, right? Let's say we have observed this. So let's say I have taken one employee, or let's say I have taken myself, and every day I'm just taking down the number of minutes I took. So let's create a table. Let's create a set over here. This is my observed set for x. So x observed. The observed set for x is, let's say in the first day I took 11 minutes. Second day I took 32 minutes. Then let's say 23 minutes. Then let's say 59 minutes. Then let's say 43 minutes. Then let's say 29, 33, 48, 57, and 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For 10 days, I observed the number of minutes I took. Now, can I take each of them as a random variable? No, because this is a continuous random variable. So my question to all of you is that, are these the only possible outcomes which I can get from this experiment? No. We can have more outcomes. If I perform this experiment for another 10 days, I can get more values. Let's say someday I took 23 minutes 2 seconds, so 23.2. Let's say someday I took 11 minutes and 5 seconds. So there are endless possibilities. So I cannot take each entry or each outcome over here as one random variable. Then what is the solution? I would go with the range. So let's define the range over here. So range would be, let's say, from 10 to 15, 15 to 20, 20 to 25, 25 to 30, 30 to 35, 35 to 40, 40 to 45, 45 to 50, 50 to 55, and finally 55 to 60. And I will now just write down number of times I observed a value between this range or in this range. So let's write the count. So in between 10 to 15, I was having this value, which is 11 and 12. So I write 2 over here. Between 15 to 20, I don't have a value, 0. 20 to 25, 20 to 25, I'm having one value, so I'll write 1 over here. 25 to 30, 25 to 30, I'm having one value, so I'll write 1 over here. 30 to 35, so one value over here, one value over here, so two values. 35 to 40, 35 to 40, I don't see a value, so okay. 30 to 35, I was having no value, so I should write 0 over here. 30 to 35, I'm having 33 and 32, yeah, 2. So this was correct. Ignore if I'm doing something wrong, because I'm just trying to quickly fill this table. 35 to 40, 0. 40 to 45, 40 to 45, one value over here, so 1. 45 to 50, one value over here. 50 to 55, I don't see a value. 50 to 50, 55 to 60, one value over here, one value over here, so two value. Now when I plot this, I will plot it as a range. So my x is over here, which is again the time taken by an employee to commute between office to home. Here I'm having the same count, but here I will have the range. So starting from 10, 15, 20, 25, 30, 35, 40, 45, and so on till 60. And then I will have this bars, which is known as the histogram. This is not the bar chart, this is the histogram. So 10 to 15, let's say 2, like this. Then 15 to 20, I'm having 0, so a line like this. Then 20 to 25, I'm having 1 and then 1. So let's say like this. And then again I'm having 2. And then again I'm having 0. Then again 1 and 1. And so on. Now this is basically my probability density function, PDF. Probability density function. Now why I'm calling it as a density? Because if I ask you what is the probability of a person takes the time between 10 to 15 minutes, I'm not talking about one point, I'm talking about a range, which is density. So that is the reason here the distribution is known as the density. And please remember, the probability of a one point in a continuous distribution or continuous random variable is always equal to 0. If I ask you what is the probability that a person will take 10 minutes, that would be 0. The probability is 0. The reason is we cannot calculate it. We cannot calculate it because the way we are calculating the continuous random variable is by using a measure. Here we are using a measure as the time taken by a person, right? And 10 minutes is something that a person can take endless number of time. So we don't know how many times a person can take 10 minutes divided by we know. So how many times a person can take 10 minutes? The probability of 10 minutes would be number of times the person takes 10 minutes divided by total time. So total time we know, total time is 60 minutes, but how many times the person has taken 10 minutes? I don't know. The answer, this can be infinity also, right? I don't know that. So the probability will end up becoming 0. So the probability of a point in a continuous random variable is 0. And the reason we call it as a probability density function is because we are not talking about one point probability, we are talking about a range. Now within discrete random variable, the distribution for discrete random variable and the distribution for continuous random variable, we have some very general distributions, some standard distributions that are very important in the field of statistics and probability. So that is what we are going to learn next. The various type of standard distribution that comes under both discrete and continuous. So we have talked about discrete random variable and continuous random variable. And we have seen a very simple example of how we can create distributions for discrete and continuous. Now there are some standard distributions that comes under discrete and continuous. So what we are going to do, we are going to talk about these standard distributions. So the very first, we will first talk about discrete. So within discrete, the discrete random variable, we have two very important distributions. One is known as Bernoulli and the second one is known as binomial. So Bernoulli distribution and binomial distribution. Now what is the Bernoulli distribution? Or we will first talk about the Bernoulli experiment. So when we talk about the Bernoulli experiment is a particular experiment in which, number one, the outcome is always binary. So the outcome is always binary, which basically means the outcome is either head or maybe win or loss, head or tail. So let's say head or tail, win or loss, or maybe 1 or 0. So it will always be binary. The second one is the number of trials is only 1. So we are just performing the experiment for one time. So the number of trials is only 1. So for example, let's say I'm having a coin and I tossed this coin for one time. So toss of this coin for one time. Now can I consider this as a Bernoulli experiment? Yes. Why? Because when I toss this coin, I may either get a head or a tail. So the outcome is binary. Now since the outcome is binary, this experiment is the Bernoulli trial. So why I'm calling it as a trial? Because I am performing the experiment for one time. So I can either get head or tail. So the Bernoulli distribution looks like very simple. We have already seen it, but I'm drawing it again. Let's X represent the number of heads when you toss a coin for one time. So you may either get a head. So let's say I obtained a head, and for tail it is nothing. So this is basically my Bernoulli distribution. Bernoulli distribution. Now please remember one thing, there is nothing difficult to remember about Bernoulli distribution. It is just a particular experiment which is having binary outcome and one trial. Binary outcome, one trial. Now binomial is something very much associated with Bernoulli. So when I perform the Bernoulli experiment for n number of times, then we get a binomial experiment. So what is binomial? Binomial experiment. So when the Bernoulli experiment is performed for n times, we get binomial experiment. We get binomial experiment. This is my binomial experiment. Let's take one example. Let's say I'm having a bag and we will try to understand the binomial experiment. So binomial experiment is nothing but when I am performing the Bernoulli experiment for n times, it becomes binomial. Again, the outcome of each trial in binomial experiment is binary. So again, assume that you are having a coin and you are tossing it for 10 times. So since I am tossing it for 10 times, it becomes binomial. But the outcome of each trial is going to be either head or tail, which is binary. And that is the reason it is a binomial experiment. So we have n Bernoulli experiments. When I combine them, it becomes binomial. Now let's understand how to calculate the probability of binomial experiment. So probability of binomial experiment. Okay. Now let's say I'm having a bag and this bag is having, let's say, 2 orange balls. So 2 orange balls. So let's say the bag is having 3 orange ball and 2 white balls. So 1 white ball, 2 white balls. So 3 orange and 2 white. Now my random variable x is the number of heads, my random variable x is the number of orange balls I may get out of this bag. Number of orange balls I may get out of this bag if the experiment is performed for 3 times. Now, if you are not able to understand it, let's try to take the example. So the experiment is, we have to take the ball out of the bag, note down the color. So what's the color? Orange. We will note it down and put the ball back to the bag. And I will do this for 3 times. Now, is this a Bernoulli trial? When I'm taking the ball out of the bag for 1 time, is it a Bernoulli trial? Yes. Why? Because I can either get a orange ball or not get a orange ball. So first time I obtained a orange ball. This is my one Bernoulli trial. And I place the ball back to the bag. Again, I did the experiment. I obtain again a orange ball. And I note down the color. I put the ball back to the bag. And I did it again. I again take a ball out of the bag. It came out to be orange. I note the color and I put the ball back to the bag. Now what is happening? I have performed the Bernoulli experiment for 3 times. So each time I was taking the ball out of the bag, it was a Bernoulli trial. and I have performed the Bernoulli trial for 3 times. So let me just note down the outcomes. First of all, let me note down the experiment. The experiment is, take a ball out of the bag, then note down the color of the ball, and then put the ball back to the bag, back to the bag. Now we have to perform this experiment for 3 times. Now we have understood the experiment, right? Now let's say I'm interested in finding out the probability that I will get exactly 2 balls when I am performing this experiment for 3 times. So 2 orange balls, 2 orange balls in 3 trials. Now what are the possible combinations in which you can get 2 balls or 2 orange balls? Let's note it down. So this is my trial number 1, 2 and 3. Let's say for the first 2 trials I obtained orange. So let me write OO, and then you obtained a white ball. So white. Then for the first you obtained orange, then white, then orange. Then for the third you obtained white, then followed by orange and orange. So now these are the 3 possible combinations I may get out of this experiment. Now what is the experiment? I am taking a ball out of the bag, noting down the color, putting the ball back to the bag, performing this experiment for 3 times. My objective is to find out the probability that I will get 2 orange balls in 3 trials when I am performing this experiment for 3 times. These are the 3 possible combinations. Now if you carefully observe, each trial is independent of the other, because every time I'm taking a ball out of the bag is still having 5 balls, because we have total of 5 balls, right? So what is the probability of getting orange, orange, white? It will be simply probability of orange multiplied by probability of orange multiplied by probability of white. Similarly for this, orange, white, orange would be probability of orange multiplied by probability of white multiplied by probability of orange. Then white, orange, orange would be probability of white multiplied by probability of orange multiplied by probability of orange. Now probability of orange is 3 divided by 5. Probability of orange is 3 divided by 5. Probability of white ball is 2 divided by 5. So this will be 3 by 5 into 3 by 5 into 2 by 5. This will be 3 by 5 into 2 by 5 into 3 divided by 5, and this will be 2 by 5 into 3 by 5 into 3 by 5. So if you carefully observe, I can write each of them as 3 by 5 to the whole square into 2 by 5. I can even write this as 3 by 5 to the whole square into 2 by 5. I can write this as 3 by 5 to the whole square into 2 by 5. Now what is the probability of getting 2 orange ball in 3 trials? I am having 3 possible combination. So it can be either this or this or this. So when I am having an OR term, that basically means I have to add all of them, right? So it will be probability of O, white, which is plus probability of orange, white, orange, plus probability of white, orange, orange. Now we have already calculated everything. So it is, I'm just taking it over here. So it will be 3 by 5 to the whole square into 2 by 5 plus 3 by 5 to the whole square into 2 by 5 plus 3 by 5 to the whole square into 2 by 5. Now all the 3 terms are similar, so we can just simply write it as 3 times of 3 by 5 to the whole square into 2 by 5. Now, this particular equation can be generalized for any binomial experiment. How? Let's see. The generalized equation is ncx px q to the power n minus x. This particular equation can get you the probability of any binomial experiment. What is n? N is the number of Bernoulli trials. X is the number of success in n trials. P is the probability of success, and Q is the probability of failure. So if I try to map this equation for this particular experiment, where I have calculated the probabilities 3 times of 3 by 5 to the whole square into 2 by 5. Let's try to do it in next slide. So the formula is ncx px q to the power n minus x. Now, in the last experiment, we were performing the trials, Bernoulli trials, for 3 times. Here I have written it, right? So my value of n is 3. Now what is x? X is the number of success. Now if I consider getting an orange ball as a success, then I was interested in getting 2 orange balls, right? So my x is 2 because I am interested in getting 2 orange balls. Probability P is probability of success, which is nothing but probability of orange. And orange probability is 3 by 5. And Q is the probability of failure, which can be also written as 1 minus P. This is given as 2 by 5. Now if I put everything on the formula, this will be 3C2 3 by 5 to the 2 into 2 by 5 to the power of 3 minus 2, which is 1. The ncx factorial, this particular term can be expanded as n factorial upon x factorial, n minus x factorial. So 3c2 would be 3 factorial upon 2 factorial, 3 minus 2 factorial, which is 3 into 2 factorial divided by 2 factorial into 1 factorial. 2 factorial will cancel out 2, so we'll be left with 3. So 3 times of 3 by 5 to the whole square into 2 by 5. And here you can see we have already done this manually. So using this formula, you can find out the probability of the number of success in n Bernoulli trials. The number of success, which is x, in n Bernoulli trials, which becomes binomial, right? Let's take one more example, a quick example to help you understand this. So I'll just create a portion over here. So let's say there is a person who is trying to shoot a target. Here we have a person. This person is trying to shoot a target for 10 times. For 10 times. So n is 10. Now, is this particular experiment consist of a Bernoulli trial? Yes, because when the person is trying to shoot the target, it will either hit or miss. So it is a binary experiment, which is the outcome is binary. And if I consider the experiment to be performed for 1 time, it is a Bernoulli trial. Since I am performing this experiment for 10 times, it becomes binomial experiment. So let's say the person is trying to hit the target for 10 times. The probability that he will make a hit is let's say 0.4. So there are 40% chances that if a person try to make a hit to the target, it will hit the target 40% of the time. So the probability of miss will be 0.6, right? Now I'm interested in probability that he hits the target exactly for 5 times. So I'm interested in 5 success in 10 Bernoulli trials. So my x value will be 5. I quickly apply the formula n cx px q to the power n minus x. N is 10, c 5. Probability of hit is 0.4 to the power 5 and then 0.6 to the power of 5. You can solve this and you will get your answer. What is the probability that if the person is trying to hit the target for 10 times, he will make a hit, he will make an exact hit for 5 times, and this will be your probability. This is the binomial probability. Now, if I calculate all the probability for all the random variables, in this case, in the case of hitting the target, what is my random variable? My random variable x is the number of times this person makes a hit. Now the person can make a hit for all the 10 times, for 9 times, for 8 times, for 7 times, 6 times, or maybe for 0 times. So these are all the random variables. Now against each random variable, if I calculate the probability and I plot them, so let's say here I'm having x, here I'm having probability of x is equal to xi, and if I calculate all the probability, what is the probability that he will hit the target for exactly 10 times, for 9 times, for 8 times, for 7 times, and so on. And if I plot it in a mass function, so here I'm having x, here I'm having, let's say, probability p of x is equal to xi, then this will become my, this will basically become my PMF of binomial probability or binomial experiment. I hope everyone is clear about this. We can have a quick Excel example to demonstrate you how this particular PMF looks like. So let's look at an Excel example. Now here I'm having an Excel worksheet. Let's say this is my x, which can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. What is the meaning of 0? That basically means a person was not able to make any correct hit. So if the person was trying for 10 times, he was not able to hit for any time. The number of successful hits was 0. What is the meaning of 1? 1 basically means when the person was trying to hit for 10 times or maybe shooting for 10 times, he was able to hit the target only for 1 time. So that's what my x is. I'm now interested in calculating the probability of x is equal to xi. So let's do that. We will use the formula, the combination formula. So combine is the function that we have in Excel, and the total number of trials are 10. X is this multiplied by, so NCX, probability of success was 0.4 to the power of x, 0.4 to the power of x, and I will put this in a bracket so that nothing is getting wrong, and this is multiplied by failure, so Q, so 0.6 to the power of n minus x, so 10 minus x, and I close the bracket and I think everything is fine. Let's expand this formula. I have the probabilities. Now let's plot it. So I'll go to insert. I'll choose a chart, maybe a column chart. And here we have the probability, which is wrong. Actually, it is plotted very wrong. I should choose only I think if I choose this also, let me try it for one more time, otherwise we have to manually do it. Okay, it is not coming correctly, so let's choose only this one. Insert and this chart. Now here, first of all, this is not 1, this will be 0, this will be 1 because we haven't selected the x. So assume this is 0, then this is 1 and so on. Now you can see that the probability that a person will hit for 4 times is highest. 4 times is highest, and here you can see in the result also that the person hitting the target for 4 times is highest, and then as we move forward it becomes lower and lower and lower, and if I go below 4 it is becoming lower and lower and lower. So using the probability mass function of any discrete random variable, we can answer a lot of questions. So if I ask you, what is the probability that the person will be able to hit, or the person will be able to make at least 5 correct hits, or at least 5 successful hits? So at least 5 means I am interested in the probability of x greater than or equal to 5, which basically means I'll just simply take the summation of all these probabilities, which is equal to 0.36. So there are 36% chances that the person will hit at least for 5 times. What is the probability that the person will be able to make the correct hit at most 5 times? At most means less than or equal to 5, which basically means I am interested in all these probabilities, which is 83%, which basically means the person will be able to make at most 5 correct hits 83% of the time, right? Now using this PMF of various distribution, various discrete random variables, we can answer a lot of questions, right? And that is the reason these distributions are created. But we are interested in one such distribution, that is I would say that is a very important distribution in the entire statistics and entire machine learning. That is known as the normal distribution, which comes under the continuous random variable. So we have completed a discussion around discrete random variable, under which we talked about Bernoulli experiment and the Bernoulli distribution, then binomial experiment and the binomial distribution, and this is the binomial distribution. Now let's talk about the continuous random variable, and within that the most important distribution is normal distribution. If you guys are targeting for any data science job and you have to attend your interview for the data science field, then this topic is one such topic that you will 100% find out in your interview. It can be in any way, but it will be around this topic. So please listen to me very carefully, because this is really important when it comes to data science interviews. So when it comes to continuous random variable, we have a distribution known as the normal distribution. And normal distribution is something that looks like a bell-shaped curve, something like this. Now, what is the meaning of this? So if I assume that the x-axis represents income and the y-axis represents the count or the probability, then within this range, I have highest number or the highest occurrence of the observations. So I have maximum number of people in the mid range, in the mid income range. This is known as the center of my distribution. Now, what I have drawn right now is a normal distribution, but in reality, normal distributions can be of variety of shapes. As of now, you can see it is a very symmetrical shape, but in reality, you might get a very symmetrical shape of a normal distribution or you might not get. So in order to understand whether your data is following a normal distribution or not, we have something known as the standard normal distribution. Now, why we have a standard normal distribution? A standard normal distribution will help you to compare few properties in your original data. So let's first of all understand what is a standard normal distribution, what are the properties of standard normal distribution, and then we will try to compare our data with the standard normal distribution to generate some insights. Let's try to understand the standard normal distribution. Now here I am having a particular standard normal distribution. The advantage of standard normal distribution is that it is perfectly symmetrical, which basically means this is my center, this is my center, which basically means this is having the mean, this is my mean point. So mean, median, and mode, all the three quantities fall in the center. I'm having 50% data below this, 50% data above this. So it is perfectly symmetrical. Half here in the left side, half here in the right side. Now, the numbers you look into the x-axis are known as the z-scale. We will talk more about it. Don't worry, I will explain you everything. What is z-scale, how we got these numbers, don't worry. As of now, just try to understand what is a standard normal distribution. So number one is the mean and the median and the mode, all these three properties lies in the center. It is perfectly symmetrical, 50% on the left, 50% on the right, which basically means 50% data is on the left, 50% data is on the right. According to the standard normal distribution property, 68% of the data lies between plus minus 1 standard deviation. 95% data lies between plus minus 2 standard deviation. And 99.7% data lies between plus minus 3 standard deviation. Now what is this? This is 1 standard deviation. 1 standard deviation below, 1 standard deviation above. So between these 2 points, I am having 68% of the data. Between these 2 points, I am having 95% of the data. And between these 2 points, from this point till this point, I am having 99.7% data. If you are not able to understand how I obtained this z-scale and what I am talking about 68, 95, 97, let's try to understand it with a real example. First of all, let's try to understand the z-scale. So what is z-scale? For this, we have to jump into the topic of scaling. Now, don't worry. We have a topic which we are talking about, which is normal distributions. We have talked about standard normal distribution. We have looked into some of the properties, but there is one confusion. The confusion is what is z-scale and how we have obtained these numbers, and what is 1 standard deviation below, 1 standard deviation above. So we will pause this topic as of now. Just create a barrier over here. We'll try to understand this small topic, which is scaling and the z-scale. Once we are clear with this, then we will bind everything and you will be very much clear. So stay with me for another 10 minutes and you will be clear with everything. So what is scaling? Now the problem is, let's say I'm having 2 variables, age and income. Let's say age is, a person is having age of 27 and income of $1,000, something like that. Now can I compare these 2 values? Can I say this is a very low value and this is a very high value? No, essentially we cannot. Why? Because both of them are having a different scale. Age is in the scale of year, while income is in the scale of dollars. So I cannot compare these two values. They belong to two different scales and we cannot compare them, right? But what if I want to compare them? Then we have to make them into a common scale, right? And that is what scaling is known as. So scaling is a process of converting the data into one common scale using which I can compare various values. There are two common approach which we follow in scaling. One is known as the min-max scaling, also known as the normalization scaling. The second one is known as the standardization or the z-scaling. The z-scaling. In the min-max scaling, I try to convert the complete data into a scale of 0 to 1, where minimum is 0, maximum is 1. The formula is very simple, x minus min divided by max minus min. I'll show you the example in Excel. As of now, just look into the formula where x is the value I want to convert. So x is the value we want to transform or convert. Now here in z scaling, the formula is x minus standard deviation, x minus mean divided by sigma. What is x? X is the value we want to convert. Mu is the mean of the column, mean of the variable, and sigma is the standard deviation of the variable. So we have this formula. Now let's try to apply this formula in actual data in the Excel file to make sense out of it. And then you guys will be very clear about how we obtained this y-axis. This is the major question, right? We have the normal distribution, standard normal distribution topic parked as of now. We are trying to understand scaling. And the main question that we are trying to answer right now is how this z-scale came into picture. And once we are clear with this, then this standard normal distribution will make more sense to you, right? So keep this topic parked. We are talking about this topic and now we are moving forward to understand the scaling topic in Excel with particularly a data example. So let's do this. Now here you can see we have a data which is having age, BMI, and charges, the insurance charges. I cannot say that this value is very low, this value is middle, and this value is very, very, very high. Why? Because age is in year, BMI is in kg per meter square. If you know, BMI unit is kg per meter square, and charges are in dollars. These all three are in different scale. I cannot compare them, right? Let's try to use min-max scaling. So for min-max scaling, I need the minimum value. So let me insert quickly some rows. So let's say here I'm having minimum, maximum. So I'm just calculating the minimum for age. Is equal to minimum of the column age. So I'm having the minimum value to be 18. Then calculate the maximum of the column age. The maximum value is 64. Similarly, I'll call this column as age underscore normal. Similarly, I'll do it for BMI, BMI underscore normal, and then for charges, charge underscore n. I'll just find out the so let's quickly do one thing. Let's shift these columns. And let's shift this column also. So that I can simply just extend the formula and I do not have to write it again and again. Now if I just simply extend this formula, I get the minimum of age, BMI and charges, and this will give me the maximum of age, BMI and charges, because age, BMI and charges are one after the other. So I just extended the formula, right? Now let's apply the formula is equal to x, which is this value I want to convert, minus minimum. So I'll just freeze this value. So I will put a dollar x minus min divided by the value max and then minus and then min, and I will, so let's do one thing, let's not freeze I, so that if I extend the formula this is not getting fixated. I'll just fix the row $4 and $3 and let's enter. Let's try to apply it on the entire column and let's try to extend it to BMI and charges also, and let's try to extend it to all the rows. Now all these three columns are in a scale where minimum is 0, maximum is 1. So assume that you have a number line, minimum is 0, maximum is 1. Now the middle point will be 0.5. So the mean is 0.5. So any value which is close to 0, you can assume that the value is very low. Any value which is close to 1, you can assume that the value is very high. Any value which is around 0.5 is the average value, right? Now the scale is very clean. And all these three columns, age, BMI and charges, are now in this scale, the normalized scale. Let's try to compare the value. If I look at this person, the age of this person is 0, which basically means this person is the person who is having the lowest age in my data. The age is 0 means the person is having the lowest age, the minimum age. Then 0.47 is the BMI, which basically means the BMI is around mean. As I told you, 0.5 is the middle, 0.47 is near to 0.5, right? So BMI is around average, while the charges are 0.009, which is very close to 0, right? So what I can conclude for this person is a young person, very young, having average BMI and very low charges, right? Let's take one more person. Let's say this person. The age is 0.91, which is close to 1, right? 0.91 is close to 1. So age is 0.91, BMI is 0.26, close to 1, 0.1, so 0.26. And then charges are 0.4, which is close to the middle value. So if I talk about this person is having very high age, not very high BMI. So BMI is below average, but charges are around average, right? Let's talk about a person who can be a outlier or something. Let's see if I can find out some interesting value so that it makes some real sense. Okay, if I look at this person is having 0.5 as age, middle age. The BMI is for this person is below average, but the charges are very high for this person. You can see this person, right? So I hope now you guys are able to understand how to read values in a normal scale. Now normal means minimum is 0, maximum is 1, and the formula is x minus min divided by max minus min. In the z scaling, which is standardization, we need the average, we need the standard deviation, and once I do this, let's do this first of all. So this will be my age hyphen z, and this will be my BMI hyphen z, and then charges hyphen z. Now let's apply the formula is equal to, so first of all we have to calculate the mean, so is equal to average. I need average of the age column. I will just extend this formula to the next cell, next two cells. Then I need the standard deviation, so I'll just use this standard deviation of the BMI age column. Then I will extend this to the next cell, and now we will apply the formula is equal to x minus mean, so x minus mean, and I will again just freeze the row x minus mean divided by standard deviation. This is my standard deviation. I will freeze the row and enter. Now let's extend it to all the rows. I don't know why it's not happening. Let me try it one more time. Okay, I don't know why it's not happening, so I have to do it manually. And then I will extend this formula to the next column also. So let's do it like this. And this one also. Okay. Now in the z scale, in the z scaling, my middle point is 0. Then I'm having -1, -2 over here, +1, +2, and +3 over here, and -3 over here. What is these values? What are these values? These are known as my standard deviation. This is my mean. So standardization or z scaling will convert your data in such a way that now the data is having a mean of 0 and the standard deviation of 1. So if you get a value close to 0, that basically means you are in average. If you go on the positive side, you are moving above average, and the higher you move, that many standard deviations you are above the average. So if, let's say the value is plus 1.2, which basically means you are one standard deviation above the average. If let's say the value is -3, that basically means you are 3 standard deviations below the average. So z scaling will convert your complete data into a scale where the center becomes 0, the mean becomes 0, and the standard deviation becomes 1 unit on either side. For min-max scaling, it was something like this, 0, 1, and middle is 0.5, right? Let's quickly compare it and try to check the z-scale. So here, if I look into this person is having BMI of 0.5. 0.5 means very close to 0, right? So 0 is the middle, 0.5 is very close to 0. Then minus 1.5 is the age, which basically means from 0, the person is 1.5 standard deviation below the mean. Then minus 0.9 charges. From the mean, the person is 0.9 standard deviation below the mean. So this person is having normal BMI because the value is close to 0, very low age, and very low charges, because both the values are on the negative side. So you can see that with standardization, since I'm having positive negative sign and middle is 0, it becomes very easy for interpretation. If the value is positive, I know this is above average. If the value is negative, I know this is below average. The value is positive, which basically means it is close to 0. That is the advantage of standardization. Now this is the z-scale which you guys can find out in my standard normal distribution. So if I go back to my standard normal distribution, this is what the z-scale is. So the middle is 0. I have one standard deviation below the mean, one standard deviation above the mean, and so on. Now according to the property of standard normal distribution, it states that 68% of the data is plus minus 1 standard deviation above or below the mean. 95% data is plus minus 2 standard deviation. 99.7% data is plus minus 3 standard deviation. Let's try to quickly prove it. Let me prove it. For that, first of all, we have to check which particular column among age, BMI and charges follow normal distribution. So I already know that BMI follows a normal distribution, which basically mean when I plot it, it would resemble a normal curve, a bell-shaped curve, which is symmetrical. You will get half data from below the center and half data above the center. And since I have converted the BMI column completely into a z-scale or standard scale, now just see the magic. I have selected the BMI column, and now we will go to the insert option in this Google Sheets, go to chart, and we will select the histogram. Now if you closely observe this histogram, you can see that this point is the center. 0.03 is the center, and below this value I'm having negative points. Above this value I'm having positive points. Now you can see that the data is spread around minus 2 standard deviation, which basically means below it is distributed 2 standard deviation below the mean and 4 standard deviations above the mean. Now you can see that it is not perfectly distributed. 2 standard deviation below, 4 standard deviation above. So here I'm having less data, here I'm having more data, or the spread is more on this side, the positive side. So this is one thing which can understand. This is a normal distribution, but this is not standard normal. So in order to compare this distribution with something, we need a standard thing, right? Let's say if I have to compare my performance in any exam, I need some standard score, right? Standard score is 100. So maximum is 100. The best is 100. So whenever we try to compare something, we need a standard, right? Similarly, in order to compare the distribution of a continuous random variable which appears to be normal, I need a standard normal distribution, and this is where my standard normal distribution comes into picture. This is my standard normal distribution. Now standard normal distribution says that your mean, median and mode will lie in the center. And if it is not lying in the center, if your mean is not equal to mode is not equal to median, your distribution is not standard normal distribution. It will be either left skewed or right skewed. These are the two terms which I am introducing. I will explain you as we move forward, don't worry. But as of now, we are trying to understand the properties of normal distribution. And here I have already written the 3 properties, which is 68% of the data lies across plus minus 1 standard deviation above or below the mean. Similarly, 95%, 2 standard deviation above or below the mean, and 99.7% data lies across plus minus 3 standard deviation, right? Now what we are going to do, we are going to quickly prove it. So here we have the data. I'll just quickly close this. I'll copy this data into a new sheet over here. Now we will calculate the mean, median and mode. And for simplicity purpose, let's not use the z-scale, let's use the original scale, so that you guys are able to understand this. So I'll just replace this column with the original data, BMI. What is the average BMI is equal to average of this column. What is the median? So MEDIAN, median of this column. And what is the mode? MODE, mode of this column. And here we have, so now you can see that mean is 30.6, median is 30.4, mode is 32.3. These values are approximately close to each other, not exactly same. So first impression about this distribution is that it is not standard normal distribution, but it's something close to standard, right? But how much close? Let's try to understand that. First, we will prove the property. The property is that 68% of the data falls across plus minus 1 standard deviation, right? So let's quickly find out the standard deviation. So STD DEF is equal to STD. So this is my standard deviation of this data. It is 6.09 standard deviation. If I go plus 1 standard deviation below the mean, so let me create a table over here, 68%. I go, so this is my mean minus, let's say, this is my lower limit, this is my upper limit. I'll explain you everything, don't worry, don't get overwhelmed. And this is my count, this is my total, and let's write 68% over here, and this is mean, so 1 standard deviation. So now what we are going to do, we are going to take mean and subtract 1 standard deviation. So 1 standard deviation, so mean minus 1 standard deviation. The lower limit is 24.5, then mean plus 1 standard deviation. The upper limit is 36. Now I will count how many values are falling in this range, because my objective is to find out the percentage. So I'll quickly apply a filter over here, and I will create a filter by condition, and my condition is between the lower value is 24.5 and upper limit is 36.7, and I'll just quickly create a filter. Now I'll just simply count it. If you carefully look over here, the count is 900. So there are 900 values that falls in this range. What are the total number of values? For that I have to remove this filter. So I'll say none, I'll say okay, and I will calculate. So 1338 is my total. So 1338. Now let's calculate the percentage. Percentage. So my percentage is equal to count divided by total, and this is 0.67. If I convert this into percentage, it is 67.2%. The standard value is 68%. My data is resulting in 67.2%. This is the first proof of the first property. The first property says that 68% data lies between plus minus 1 standard deviation. I am getting 67.2 because it is not standard normal, right? The second property is 95%. So 95% data lies between plus minus 2 standard deviation. Let's check the lower limit. So is equal to mean minus 2 times of the standard deviation, then is equal to mean plus 2 times of standard deviation. And now I will count. So I will go over here. My condition is between, my lower limit is 18.4, upper limit is 42.8. I'll click OK and I will now count. The count is 1281 data points, 1281. So let's quickly write it down over here. 1281, 1338 is my total. I'll just extend this formula to the next, the below cell, 95.74. What is the standard value? 95%. What I am able to achieve? 95.74. Why there is a difference? Because BMI is not my standard normal distribution. According to the standard normal distribution, around 95% values in my data point will lie between plus minus 2 standard deviation, and here you can see final one is 99.7% of my data falls between plus minus 3 standard deviation. So is equal to mean minus 3 times of standard deviation is equal to mean plus 3 times of standard deviation. Now I'll calculate how many data points I'm having in this range. So 12.3 to 48.9, and I'll click OK. I'll just quickly count. It is 1334 and total is 1338. So 1334, this is 1338, and I will extend this formula to the next row, and I'm getting 99.7, which is exactly the same, right? So this is the proof of these three properties, that 68% of the data lies between plus minus 1 standard deviation, 95% plus minus 2 standard deviation, 99.7 in plus minus 3 standard deviation. Now, if I am given with a particular value, so let's say I am given with a particular value, how I can find out that what is the probability at that point? If you are not able to understand my question, don't worry at all. Let me try to make you understand what I'm asking you. This is my standard normal distribution. This is my middle point, which is 0. 0 means the mean is 0. What is the probability that a data point will lie below this point? What is the probability? It is 0.5, and above this point it is 0.5, because as you already know that if I'm having if I consider the complete probability, so what is the probability that a data point will lie anywhere in this particular range? It is 1, right? We know the minimum range, we know the maximum range. I know the probability that my data will lie somewhere in the middle, so I know it is going to be 1. What is the probability that it will lie below mean? 50%, above mean 50%, if it is a standard normal distribution. So in order to find out the probability at any point from the left, we have something known as a z-table. Z-table is basically a standard normal distribution table. A standard normal distribution table which helps us to find out the cumulative probability from lower point to this point. If I ask you what is the probability that a data point will lie below this point, so using the z value, so let's say the z values over here is -1. So using the z table, we can find out this probability, which is the area under the curve. Now let's see one example. Let's say a set of biology marks in a class are normally distributed with a mean of 70 and standard deviation of 6. Standard deviation of 6 points. Now let X represents the score on randomly selected person. So let X represents the score of a randomly selected student. Then what is the probability that the marks of this student would be between 64 to 79? Now this question is very simple to solve. We just need the properties that we have learned. Let's create the normal distribution first of all. This is my normal distribution. The mean is 70. Standard deviation is 6, which basically means I'll go one standard deviation below, so I'll get 64, one standard deviation above, so I'll get 76. 2 standard deviation below, 58. 2 standard deviation above, 82. Now what I need the probability between 64, which is this point, 64, which is this point, to 79, which is between 76 and 82, right? So from 76, if I go half standard deviation above, this will be 79, right? So this is the area which I am looking to find out. Let me just highlight the area. This is what I am looking to find out. I hope you guys are able to look at the area. It looks like I am coloring a book, but I hope this makes sense. Now this is the area which I am interested in. Now if I go with the logic and the properties that we have learned, so from this point till this point, my the percentage of data points, or the probability of a data point between 64 to 76 is 0.68, 68%. We know the property, right? Now from this point till this point, from this point till this point, and from this point till this point, what is the area under the curve? So if this is 68, then this point will be, or let's not look at the complete curve, let's look at the middle portion only. So from 58 to 82, from 58 to 82, so probability of data point between from 58 to 82 is 0.95, 95%, right? If I subtract this middle portion, this point, I will get this portion and this portion, and I need the half of this portion, right? As we know that this part and this part is going to be exactly the same, right? So let's call this as C, and let's call this as C. Let's say 0.68 plus 2C is equal to 0.95. So 2C is equal to 0.95 minus 0.68. C is equal to 0.95 minus 0.68 divided by 2. This will give me C, this part, right? So let's calculate C. So this will be 0.135. Now I am interested in half of it, right? So my final answer will be probability of a data point between 64 to 79. I'm interested in this point, will be 68, which is 0.68, plus 0.135 divided by 2. So 0.68 plus 0.675, which is 0.7475. This is my final answer. So there are 74.7% chances that a person who is randomly selected in the class will have the marks between 64 to 79. Now, in order to solve this question, we have used just the property of a normal distribution, which states that 68% of the data lie between plus minus 1 standard deviation, 95% between plus minus 2, and 99.7% plus minus 3. I hope this is making sense, right? Now let's take one example which will utilize the Z table, for which in order to solve this we need the Z table. So the question says the scores of ZMAT or GAMT, ZMAT are roughly normally distributed with a mean of 527 and a standard deviation of 112. What is the probability that of an individual is scoring above 500? So my first question is probability of an individual is scoring above 500. Now in the previous question we were able to solve it because the numbers that was given in our question was in the terms of n standard deviation. So the standard deviation was 6 units. I was given the minimum and the maximum range in such a way that I was able to make calculations. I was able to use elementary math to get to the point, right? But now we are not able to adjust it because 500 and then standard deviation is 112. It is really difficult to use the logic and use elementary math to get it done. In this case, Z tables are very useful. Let's solve this question. I know that the ZMAT scores are normally distributed with the mean, which is 527 and standard deviation is 112. Now I will find out how many standard deviation above or below this value is lying at. So we will use the standardization formula. We will find out the corresponding Z value, which is nothing but x minus mean divided by sigma. X is 500, the value to be scaled, minus mean 527 divided by 112, which will be minus 0.24. So if I consider the Z scale, this value will be 0 and minus 0.24 is over here below mean, minus 2.24. Now what is the probability that the person will be able to score above 500? In which area I'm interested in? So if this point is minus 0.24, then I'm interested in the area above this, which is this area. The probability that the person will be able to score above 500. So I'm interested in this area, this particular area. Now how we will find it out? So using the Z table will provide me the area under the curve from this point all the way up to this point. Remember, AUC that you will get from the Z table will always be from the left. So once I have the area, which is the probability from this point all the way up to this point, I'll subtract it from 1 and I'll get my required answer. Let's check the Z table. Now here we have the Z table, and if you read, this is the standard normal distribution. Table value represents area to the left of the Z score. So if this is my Z score, left of the Z score. I'm interested in the value which is minus 0 point. So let me just cross check it. Minus 0.24. Let's check the area under the curve. So minus this is 0.2. So we have to first read the row and then the column. So minus 0.2 and then 4, this value over here. So minus 0.24, the intersection of these two values will lie over here, I think. Yes. So this is 0.40517. 0.40517. So this x is 0.40517. I'm interested in this. So what it will be is equal to 1 minus probability of x less than or equal to 500, which is 1 minus probability of 0.40517. The answer will be 0.59. There are 59% chances. Let's say there is one more question in the same example. How much minimum marks should the individual score in order to be in the top 5%? Now this is a very interesting question, and if you guys can understand it, you have understood the complete normal distribution. Top 5%. If this is my middle value, top 5% means below me or below that point 95% data is there. So if I draw the normal distribution and below, so let's say this is the point which I want to find out, and below this point I'm having 95% of my data, right? So I know that I want to find out that z value, x minus mu divided by sigma. I need to find out that x where the z value is this. So what is the z value at 95%? Let's look into that. The z value at 0.95. So I have to look at the area now to find out the z value. So 9505 is over here. This is 1.6 and 5. So 1.65 is my z value. So the z value over here is plus 1.65. So I know the z value plus 1.65 is equal to x minus mean is 527 divided by standard deviation is 112. Again the elementary math, 1.65 multiplied by 112 is equal to x minus 527. So my x will be 1.65 multiplied by 112 plus 527, and this would be 710.6, which basically mean the person has to score a minimum of 710.6 so that the person can lie in the top 5%, and below that person I am having 95% of the observations. Now this is the application of z-table. How z-table can help you to find out the z values, and how z-table can help you to find out the area under the curve, which is essentially the probability. What is the probability that I will have a data point below this point, below this z value? That's what the application of z-table is. Now we have learnt about a lot about standard normal distribution, right? Now what we are going to do, we are going to learn last property of standard normal distribution, which is the analysis of skewness. We know that a standard normal distribution looks something like this. A bell-shaped curve which is symmetrical, which basically means 50% data below mean, 50% data above mean. But this is standard, and in reality it is very difficult or close to impossible to find out a random variable, a continuous random variable which appears to be a standard normal distribution. So we use standard normal distribution as a benchmark, but in reality you may get a distribution which is either left skewed, right skewed, or no skewness or near skewness. let's look at all the three types. This is known as the left skewness. I apologize, this is known as the right skewness. Right skew. Why I'm calling it as right skew? Because the skewness is on the right side. So right skew. In the case of right skewness, this tail happens to be because of the presence of outliers. The presence of outliers. Presence of outliers. While most of my data is on the lower side. So here I will get the mode followed by the median, and then I will have the mean. So I hope you guys remember that when we were talking about the descriptive statistics, we have learned that if I'm having outliers on the higher side, my mean will shift to the higher end. And that is the reason you can see that the mean has shifted to the outliers or towards the outlier. Now below this point, below the median, I will have the 50% of my data, and above this I will have 50% of my data. This is known as right skewness. I can also get a distribution which is left skewed, something like this. Now here again, you guys can easily understand this tail is because of the presence of outliers. Presence of outliers. And then again, this is the mode. The mode. We have the median somewhere around here. And finally the mean. So mean again shifted towards the outlier. Now here most of my data is on the higher side. If I consider this x-axis to be my income, then this left side graph represents that most of the people are having low income, while in the left skewed graph or left skewed distribution, we can understand that most of the people are having high income, but due to the presence of few people who are having low income or very low income, the graph has been, or the distribution has been skewed, and we obtained a left skewed graph. Now in the case of right skewness, my mean is greater than median is greater than mode. This represents the presence of right skewness. In the left skewness, my mode is greater than median is greater than mean. This is the presence of left skewness. And in the case of no skewness, mean will be equal to or approximately equal to median, will be equal to or approximately equal to mode. If you are getting something like this, you can say your distribution is close to normal distribution. Close to normal distribution. Now please remember the properties that we have learned, 68%, 95%, 99.7%, which is also known as 1, 2, 3 rule. It will be best applicable if your distribution is close to normal distribution. While if your distribution is having left skewness, right skewness, well, those properties will not be 100% true. It will be close. It will be very close. Sometimes it will be very different. So whenever you are applying the property, please make sure that your distribution is close to normal distribution. The example of BMI that we have seen was close to normal distribution, and we can just go back to the same sheet. So let me go back to the same sheet. Here we have the data, and here you can see that the mean, median and mode were very close to each other. So this distribution was close to normal. It was not perfectly normal, it was close to normal, and that is the reason these properties hold true. Otherwise, if this distribution was not normal, these properties would not have held true. I hope this makes sense. So we have covered a lot of topics, and the most important topic that we have covered till this point was the normal distribution. the analysis of Z table, how to read a Z table, how to make use of Z table to find out the probability values. And we have also learned about descriptive statistics and a bunch of probability, the random variables, continuous, expected value. We have learned a lot, right? Now we are going to start with the second very important topic under our statistics and probability framework, which is inferential statistics. I have already given you the essence of what inferential statistics is and why we need it when we were discussing about descriptive statistics. But now we are going to understand it completely, and also we are going to utilize the power of inferential statistics to make estimations. So let's start our discussion. So when we talk about inferential statistics, in order to understand inferential statistics, we will take one example. Let's say you work for a marketing company. And your manager wants you to find out on an average how many recharge, or maybe the average recharge. So your manager wants you to find out the average internet recharge, the average internet recharge made by the Indians. So I'm talking about the complete Indians in last year. Now just look at the scope of the problem. We are talking about complete India, and your task is to find out the average internet recharge that was done by complete Indians in last year. It's a very big challenging problem, right? So let's assume that we have this circle representing the complete Indian population. So population, and now in order to find out this answer, what you will do? So let's say this is you, this represents you. You will basically reach out to each and every individual. You will collect the data. So let's say the recharge done by person number 1. So let's say the recharge done by person number 1 is R1, then R2, then R3, and so on till R, let's say 150 crore. Now first of all, it is impossible, or not impossible, to near to impossible for you to collect the data of this much size, and it will be impossible for you to perform survey in such a large scale. So what is survey? Let's say if I'm having a group of people and I want to ask whether they prefer tea or coffee. So what I will do? I will perform a quick survey. So survey basically means I will go to each and every individual. So reach out to each and every individual, then ask them about their opinion. So ask the question, then collect the data, and finally we perform the estimation. So estimation means we calculate the average, minimum, maximum, whatsoever you want to calculate. This is the process of survey. Now if I have to perform the same thing on a population which consists of 150 plus crore people, don't you think for an individual like you it is near to impossible? Not impossible to near to impossible. And the I would say it is impossible. Even for me or even for a government organization, it is impossible for anyone to perform a survey in such a large scale. Even if it is possible by a government organization, it will take a lot of time, and it will take a lot of investment. Lot of investment means lots of money is required, lot of people is required, so lots of investment. Now, what is the better solution for this? We have already discussed about it. Solution is, I'll take a small sample. We call this as a random sample. Now I'll talk about what random sample is all about. But we take a small sample, we take random people. Let's say I have taken 1 lakh random people. 1 lakh random people from the population of 150 crore plus people. Now, as an individual, it is quite possible for you to perform survey on 1 lakh people. So you have performed survey, you calculated or you collected the data. So R1, R2 till R1 lakh. Then you took the average, and this is my sample average. This is known as the statistic, sample statistic. Now using this, I will try to approximate my population parameter. So using sample statistic or sample mean, we will try to approximate the population parameter or population mean, and this is basically known as your inferential statistics. Inferential stats. Now before we talk about how to estimate the population parameter, let's try to quickly understand what is sampling and random sampling. So when we talk about sampling, it is basically the procedure of collecting few observation from a bigger subset, or you may say population. So I'm having a population. And now I want to collect a smaller sample, a smaller group of observations. This is known as a sample. Now this process is known as sampling. There is one very popular sampling technique which is known as random sampling. And this is a very important interview question. What is random sampling? Random sampling is nothing but assume that if I'm having a population having, let's say, numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So I'm having a population which is having 20 people, and the roll number of 20 peoples are written over here. Now if I have to select a random sample of 5 people, so select random sample of 5 people. So what we will do, we can select any 5 people, but according to the random sampling, the probability of selecting any observation is equal to 1 by n. So probability of selecting 1 is 1 divided by 20. Probability of selecting 2 is 1 divided by 20, and this is same for selecting any number is 1 divided by n, which basically means in simple random sampling there is no bias. We will just randomly select any observation from a population, and the probability of selecting any observation in my population is 1 divided by n, which is the same probability for every observation. So each observation in my data comes with same probability of getting selected into the sample. So here my sample can be 5, 9, 2, 7 and 10. Now why I have written 5, why I have written 9? I have just randomly selected these 5 numbers. So this is simple random sampling, and that is what I was talking about here, the simple random sample. Okay, now let's talk about how to perform estimation. In order to perform estimation, we use a particular algorithm which is known as the central limit theorem. Central limit theorem. Now what this theorem talks about? This theorem states that if I'm having a population, let's say this is a population of Indian people. Let's say I took one simple random sample of 1 lakh people. Now when I calculated the average recharge amount for these 1 lakh people for sample number 1 came out to be, let's say, 250 rupees. For again I took another sample number 2 of another 1 lakh people, the average came out to be, let's say, 220 rupees. I again took one more sample number 3, again with 1 lakh random people, the average came out to be, let's say, 210 rupees. And like this, if I keep on doing, if I take enough simple random samples from my population and I quickly plot them in a particular histogram, I'll get a normal distribution like this. I'll get a normal distribution where the average of this normal distribution is my population average, and the standard deviation is given as sigma divided by root of n. So the first property of central limit theorem is the average of all sample average will be approximately equals to the population average. The second property is the standard deviation of the sampling distribution is given as sigma divided by root of n. Now these are the two properties of the central limit theorem, and using these two properties we can estimate the population range. Let's try to understand how we can estimate the population range. Let's say this is the question that is given to us. In a simple random sample of 50 adult women is obtained. So I have a simple random sample. This sample is having n is equal to 50 women, and when the red blood cell count was measured for them, this sample average came out to be 4.63. The population standard deviation is 0.54. Now let me go back, and I did not specify that this sigma represent population standard deviation, and this n represents the number of observations in the sample. So in this case it would be 1 lakh. So central limit theorem states that the average of all these sample average. So I have taken multiple samples from my population. These are my multiple samples. 1, 2, 3 and so on. And if I take the average of all these sample average, it will be closely equal to the population mean or population average. And if I plot them, if I plot all these sample means in a distribution, in a histogram, it will closely resemble a normal distribution. and this distribution is known as the sampling distribution. This distribution is known as the sampling distribution. Why sampling distribution? Because we have obtained it using the sample means. So these are my sample means. Now, central limit theorem states that the average of all these sample mean will be closely equal to the population mean, and the standard deviation of the sampling distribution is sigma divided by root of n, where sigma is the population standard deviation and is the number of observations in the sample. Now this property is very important and very useful to estimate the population range. So I'm given with n as 50, my sigma population standard deviation is 0.54, my average sample mean is 4.63. Now I have to construct 95% confidence interval estimate. We already know that a sampling distribution follows a normal distribution. This is my sampling distribution for this particular event. So I know that my sampling distribution follows normal distribution. Let's say this is my mu, which is sample mean, and I want to estimate this range, lower value, upper value, in such a way that between these two I get 95% of my data. Now don't worry, I'm not rushing. Don't worry, I'll explain you everything. But this is my problem statement. I have to estimate the lower value and the upper value in such a way that between this I have 95% confidence. Right now we are using the word confidence, but as of now you can use the term that I need lower value and upper value in such a way that 95% data is between these two values. Now we already know this actually, that from the mean, if I go below 2 standard deviation and above 2 standard deviation, I can get 95% of my data using the second property of my normal distribution, right? But that is not exactly 2 standard deviation below the mean. I'll just tell you. Assume that this is my standard normal distribution, mean 0, and I have to find out the z value over here. What is the z value over here? And what is the z value over here? Z1 and Z2. And assume that between Z1 and Z2, the area is 95. So if the area is 95 between Z1 and Z2, this area, this black color area, what that will be? So the total sum of these two black color area will be 5%. So this will be 0.025 and this will be 0.025. How? So total is 1. Between these two data points Z1 and Z2, my area is 0.95. So I'll subtract. So I'm left with 0.05. Now since I'm having two shaded regions, I will divide it by 2. So I'm left with 0.025. So half is over here and half is over here. Now I have to find out the z value over here. So from here to here, the area under the curve is 0.025. Let's quickly use our z table. So 0.025, I have to go on the negative scale. 0.025 is over here, and this is minus 1.9 and 6. You can see it is not exactly 2, it is minus 1.96. So this point z1 is minus 1.96. Similarly, to find out z2, I have to go from here all the way up to here. So that will be 0.95. This is middle region plus 0.025. So that will be 0.975. So let's look at 0.975. So 0.975 is over here. This is plus 1.9 and 6. So we have plus 1.96. Now we have the lower z value and upper z value. From the sample mean, to estimate population range or population parameter range. Why I am estimating a range? Because if my manager is asking me to find out average recharge made by the Indians, and if I'm using sample mean, I'm not 100% sure, right? So I cannot tell my manager that the sample mean was for let's say 280 rupees, because I have just analyzed one sample. I have just surveyed one sample. So I have to tell my manager with a range, that I can tell to my manager that, okay, sir, I don't know exact value, but I'm sure, I'm 90% confident, or I'm 95% confident that my population mean lies somewhere between these two values. So that is what we are trying to estimate. So if I go back to my question, to estimate the population parameter range in my sample mean, this sample mean, we will add and subtract the z times of sigma divided by root of n. What is z? So from this value, I am moving 1.96 standard deviation below the mean, 1.96 standard deviation above the mean of the standard deviation of my sample. So essentially what we are trying to do, from the mean, from the sample mean, we are just moving below and above. So to get this lower value and the upper value. So this is my mean. In order to get 95% confidence, I will move minus 1.96 standard deviation below plus 1.96 standard deviation above the mean, and that will get me the population range. So mean is 4.63 plus minus 1.96. Standard deviation is 0.54 divided by sigma of root 50. If I solve this, 4.63 plus minus, so this will come out to be 0.149, and the range would be 4.481, 4.779. What is the meaning of this? This basically means that there are 95% chances that the actual population mean would lie somewhere between 4.481 to 4.779. So it was asking me construct 95% confidence interval estimate for the mean of red blood cell count of the adults. So right now 50 adult women were taken and their sample mean was 4.63. But if we talk about the complete population of adult women, then this range states that there are 95% chances that the red blood cell count of the complete adult woman population would lie between 4.481 microliters to 4.779 microliters. That is what this range is. Let's look at one more question, and then it will clear all your doubts and it will be very clear to all of you. So the question says you want to rent an unfurnished one-bedroom apartment in New York City. The mean monthly rent of random sample of 60 apartment advertised in some website came out to be $100. So what you did, you were trying to estimate what is going to be the average one-bedroom cost or average one-bedroom rent in New York City. So what you did, you Googled and you searched through some website. You sampled 60 apartments in the same city. So 60 apartments, my N is 60. And after looking at all the rent, the average of this sample came out to be $1,000. And the standard deviation was, you assumed that the population standard deviation to be $200. So this is just an assumption. Population standard deviation is $200. This is population. Now we have to construct 95% confidence interval. Again, for 95%, we have already calculated the z values. So the z values is minus 1.96 plus 1.96. So we will just apply the formula mean plus minus z times of sigma divided by root of n. Mean is 1000 plus minus 1.96. Sigma is 200 divided by root of 60. And if I just quickly solve this, it will came out to be 949,1050, which basically mean there are 95% chances that the actual rent of one bedroom apartment in New York City would be somewhere between $949 to $1050. And this is what the application of inferential statistics is. I hope you guys are able to connect all the dots and able to understand how we have arrived to this particular point. Now this concludes our discussion in inferential statistics. So till now we have talked about descriptive statistics, we talked about probability, and we have also looked at how we can use inferential statistic to approximate the population parameter given the sample statistic. So this is all what we have covered. Now we are going to start with hypothesis testing. Now I have already given you with a brief idea behind what hypothesis testing is. So when we started this video, we briefly discussed about all the three major buckets. What is descriptive statistics, what is inferential statistics, what is hypothesis testing. But in this section, we are going to have a detailed conversation regarding what exactly is hypothesis testing and how this can be useful when it comes to data science or when it comes to data analysis. So let's start this discussion. Now to understand hypothesis testing, we will take one example. So let's say there is a court. So let's say this particular person is the judge sitting in the court. So judge in the court. And we have two lawyers and we have the person who has been convicted. So this person is being charged for some crime. Let's say this person is talking in favor of the convicted person and this person is against the person. Now, if I ask you what will be the thought process this judge will be having in his or her mind regarding this particular person who has been charged for some crime, you guys can easily say that the judge will be having two assumptions or maybe two hypotheses or two thought process. If I tell you, like if we think in general English, it would be two thought process. Either the person is guilty or the person is innocent, right? So that is what the judge will also be having in their mind. So either the person is guilty or the person is innocent. Now, judge will decide after listening to both the lawyers, the particular lawyer who is talking in favor of the charged person, and then another lawyer who is talking in favor of in the against the charged person. So the judge will listen to both these parties, and then they will declare, or they will come to a particular conclusion, right? Now this is basically uh, you can say this is basically the framework of what hypothesis testing is. So in hypothesis testing, we have two thought process, two assumptions, and we try to conclude, we try to prove one of them. This is a very raw definition. This is not 100% correct, but the reason I am talking in this way is because I wanted to create a base of what exactly is hypothesis testing. So just keep this example in your mind, and whenever somebody is asking you what exactly is hypothesis testing, you can just generate this picture in your mind that there is a courtroom, there is a judge who is listening to both the lawyers, one in favor and one in against, and there is a convicted person. Now, either the person is guilty or the person is innocent. These are the two hypotheses that the judge will be having in their mind. After listening to the whole conversation between these two lawyers, the judge will come to a conclusion, and that is what the conclusion which we are trying to achieve, right? So the complete hypothesis framework is having two stages. Number one is to formulate the hypothesis. So given a problem statement, we have to formulate the hypothesis. So formulation of the hypothesis. And number two is the test. So we will perform the test to reject or to fail to reject one of the hypotheses. Now please don't worry about the term which I have just said, reject or fail to reject, but just remember that we will first formulate the hypothesis given a problem statement. So let's say your manager has given you a problem statement. You will first formulate the hypothesis, and then you will perform the test. Based on the test result, you will make some conclusions. So this is the simple process of hypothesis testing. So the next step is testing or performing test, and then finally conclusion. Now let's understand the formulation of hypothesis. As I have just told you that this judge would be having two thought process in his mind or in their mind. Either the person is guilty or the person is innocent. Now there is a formal word or there is a formal name given to these two thought process. One is known as the null hypothesis, and another one is known as the alternate hypothesis. Null and alternate hypothesis. Now what is null hypothesis? Now if I ask you, before this person was charged for some crime, before this person was taken to the court, initially this person was innocent, right? So null hypothesis talks about the initial state of anything, or initial state of the particular item or particular case that we are trying to test. So null hypothesis is basically the initial state of the case we are trying to test. So the initial state of this person is that this person was innocent. Before this person was taken to the court, before this person was charged for some crime, this person was innocent. Before anything happened to him, he was innocent. So my null hypothesis is the person is, so H naught. So null hypothesis can also be represented as H naught. The person is innocent. Now the alternate hypothesis is what new thing has been happened. What new we are trying to prove. The new thing that has happened to this person is this person has been charged for crime now. So this is the new thing or new state or the claim of the case we are trying to test. We are trying to prove. So HA, alternate hypothesis, can be represented as HA, and in this case it will be the person is guilty. So this is how we can formulate the hypothesis. Please remember, null hypothesis represents the initial state of the person or initial state of the case which we are trying to test, and alternate hypothesis is basically the new finding, the new thing, or maybe not the new happening which for the particular case which we are trying to prove or which we are trying to test. Now let's take few examples just to understand how we can formulate hypothesis given any problem statement. So right now this was not the problem statement. This was a very plain example. But now we will be looking at some problem statements which will have some sample mean, population mean, standard deviation to understand how we can formulate the hypothesis. Now, before we talk about some business examples to better understand how to formulate the null and alternate hypothesis, we will understand a very small topic, which is really important when we conclude. So, whenever we conclude the hypothesis testing during conclusion, we say that we reject null, or either we say that we fail to reject null. Now we never say that we accept null or we accept alternate. So what we never say we accept null or we accept alternate. Now there is a reason for this. So this is the something which I should mark in red color, because this is wrong. We never say this. Now the very first thing that we should understand is why are we only rejecting null and fail to reject null? Why it is only null? Why it is not alternate? Well, the reason is because null hypothesis is something that we know, that we certainly know. So we are 100% sure that this person was innocent before committing crime, right? Or before the person was charged for the crime, which in the court somebody is trying to prove, right? So reason we conclude on the null hypothesis is because null hypothesis is the statement which we are certain about. We know that initially this is something which actually happened. The person was actually innocent and we are certain about it. We are 100% certain about it. Now why we don't say accept null? If I say accept null, we are completely ignoring the fact that the person was guilty. Now it might be because of the lack of evidence. So if I say I accept null, I am 100% sure that the person was innocent. It might be because of lack of evidence. It might be because, so let's say this person who is talking against the charged person, he was not able to present enough evidence against the court, due to which he was not able to prove that the person is guilty. So when I say that I accept null, I am basically ignoring the fact, and I am 100% certain that this person is innocent, and I am ignoring the fact that this person is guilty, which is not true. We have to be uncertain, we have to keep some uncertainty. So the uncertainty is the lack of evidence. When we say that I reject null, I am saying that I am rejecting null, but I am not saying I am accepting null. Rejecting null means I'm not 100% sure, and it might be because of the lack of evidence. Now when I say accept alternate, the reason why I don't say accept alternate, so accept alternate basically mean that I'm 100% sure that the person is guilty. Now again, there might be the lack of evidence. The person who is talking in favor of this person was not able to collect enough evidence to prove that this person was innocent or this person is innocent. So again, when we say we accept alternate, we are completely ignoring the fact that there is some uncertainty that can happen. So in order to make sure that while we are concluding something, we have the uncertainty in our decision, and there are chances or there are possibilities of other thing happening because of the lack of evidence, we only say that we either reject null or we fail to reject null. I hope this makes sense. If it is not making sense, just remember one thing. We only say reject null or fail to reject null. We only use the null hypothesis because we are 100% sure that null was true. Null happened in reality. This person was innocent in reality. That is the reason we use null. The second reason why we do not say accept null or accept alternate is because uh, there might be lack of evidence due to which I was not able to prove the statement. So in order to include the uncertainty in my conclusion, we only reject or fail to reject null. I hope this makes sense. Now, given a particular problem statement, how we can formulate the null and alternate hypothesis? So in this particular question, it states that a restaurant owner installed a new automatic drink machine. The machine is designed to dispense 530 ml of liquid on medium size setting. Now, what is the initial state of this machine? So we know that the machine was designed to dispense 530 ml. This is the initial state of the machine. So let me just highlight this. This is the initial state of the machine. The owner suspects that the machine may be dispensing too much in medium drink. They decide to take a sample of 30 medium drink to see if the average amount is significantly greater than 530 ml. Now, what the owner wants to test if the average amount is greater than 530 ml. So this is the new finding. So my alternate hypothesis is that the average amount is greater than 530 ml. My null hypothesis will be the average amount is less than or equal to 530 ml. Now, why I am using less than or equal to? Now, please remember, in the question it says the machine is designed to dispense 530 ml of liquid. So I should have written null as average is equal to 530 ml. But please remember one thing. I hope you guys remember when we were talking about continuous random variable and the distribution of continuous random variable, we know that the point probability is 0. So is equal to 530 ml. Let's say this line is 530 ml. Now greater than 530 ml is this region. Above the line, everything is greater than 530 ml, right? This is greater than. Now if I use alternate as greater than 530 ml, and null as is equal to 530 ml, I will never be considering this region, right? The lower region, and that would not be helping us to arrive at a conclusion, right? So for example, if I'm getting a value which is lying below 530 ml, then in that case, if I do not consider this area, I would not be able to conclude anything. So that is the reason, in order to make sure that I'm covering up the complete distribution, we use less than or equal to. So we get this part also, and then we'll be able to cover up the complete area under the curve. There is one rule also, the rule of hypothesis testing, that when we talk about or when we formulate the null hypothesis, the null hypothesis always they will always be having less than equal to sign, greater than equal to sign, or equal to sign, while alternate will always have less than, greater than, or not equal to. This is rule number 1. Rule number 2 is null and alternate are 100% opposite to each other. So null and alternate are 100% opposite to each other, which basically means if in my hypothesis formulation, if I get my alternate as less than, this will be greater than or equal to. If this is greater than, this will be less than or equal to. If this is not equal to, this will be equal to. This is my alternate, this is my null. The third rule is always start by formulating alternate. Always start by formulating alternate. Now these are the 3 rules which, so if you remember them, you can formulate the hypothesis for any given problem. Let's try to look into second problem. A city had an unemployment rate of 7%. Now this is my initial state. This is something which is initially given to us, that we all know in the complete city that unemployment rate is 7%. The mayor pledged to lower this figure and supported program to decrease unemployment. A group of citizens want to test if the unemployment rate has actually decreased. So now what we want to test, or what is my new finding? Now new finding is that the unemployment rate has to be decreased. It has to go down, or it has to go below 7%. So I will start by writing my alternate hypothesis, which is average less than 7%. The opposite of this, average greater than or equal to 7%, would be my null hypothesis. Let's take one more example. E-health insurance claimed that in 2011, the average monthly premium paid for individual health coverage was $183. This is the initial statement made by the company. So this is my initial claim or initial state, initial. Suppose you are suspicious that the average or mean cost is actually higher. Now the new finding, the new thing that you wanted to test is the average is actually higher than this number. So my alternate, the average is greater than $183. Null, the average is less than or equal to $183. Simple. Let's take one more example. We want to test whether the mean GPA of students in American college is different from 2.0. Now this is what we want to test. In this question, we are not given with the initial state. So we know the alternate, that average is not equal to 2.0. Null will be the average is equal to 2.0. In an issue of US News and World Report, an article on school standard stated that about half of the students in France, Germany, and Israel take advanced placement exam and third pass. The same article states that 6.6% of US students take advanced placement exam and 4.4% pass. Test if the percentage of US students who take advanced placement exam is more than 6.6%. So there is a magazine or there is some report which already stated that 6.6% of US students take advanced placement exam. You want to test that if this number is more than 6.6%. So what you are interested in testing? The alternate will be average is greater than 6.6%, while null is average is less than or equal to 6.6%. Okay, last question. A survey was conducted to get an estimate of proportion of smokers among the graduate student. Report says 38% of them are smokers. So there is a report which says 38% of the graduate students are smokers. Now this is the initial state. This is already given in some report. This is already proven. But now Chatterjee doubts the result. Now we have a new finding. This person is suspicious. The person says Chatterjee doubts the result, think that the actual proportion is less than this. So there is a benchmark, 38%. There is a new finding in the Chatterjee. Chatterjee is thinking that the actual proportion is less than 38%. So what is alternate? That the average is less than 38%, which is what Chatterjee thinks, while the report says it is greater than or equal to 38%. This is my null and alternate hypothesis. So I hope now you guys are clear with the first stage of hypothesis testing, which is how to formulate the null and alternate hypothesis given a particular business statement. Now let's try to understand what are the various types of tests we have in the hypothesis testing topic. There are two kind of tests. Number one is known as the z-test. The second one is known as the t-test. Now within z-test, we have two methods. One is known as the confidence interval estimation or confidence interval test, also known as the z-test or the z-value method. Then we have significance test, also known as the p-value method. So within z-test, we have z-value method and the p-value method. Within t-test, we have three types of test. So these are the two methods to perform z-test. But within t-test, we have three type of test based on the problem statement. Number one is one sample t-test. Second one is paired sample t-test. And the third one is independent sample t-test. So these are the three type of test within the t-test. If I have to perform t-test, we have three type of test based on the business or problem statement. So three type of test based on the problem statement. Okay. Now, when to use z-test, when to use t-test. So I will first talk about when to use z-test. And when we will be starting the t-test, I will talk more about when to use t-test. So when to use z-test, you have to check for two things. Number one, the number of observations in your sample, in the sample, should be more than 30. And the second condition is the population standard deviation is known. Now please remember, this is a very important interview question, a very common interview question about what is the difference between z-test and t-test. I'm just talking about z-test as of now. When we start the t-test, I will show you the rules of when to use a t-test. But please remember, this is a very important topic. This is a very common interview question, the difference between z-test and t-test. So if I do not know the population standard deviation and I know the sample standard deviation, but my sample size is more than 30, then still z-test is applicable. Now directly jump to a problem statement. Let's formulate the hypothesis, apply the z-test, and let's try to conclude. In this question we are given with a sample of 40 new milk packet had an average milk content of 92.67. So within a milk packet you will find out some quantity of milk and some quantity of water. So it has been given that a sample of 40 new milk packet had an average milk content of 92.67 with a standard deviation of 1.79. So this standard deviation is the sample standard deviation. Now since my sample size is more than 40, z-test is applicable over here. Use 0.05 significance level to determine if there is sufficient evidence to support the claim that the new batch have milk content different from 92.84. Now, as of now, the complete question may be sounding really German to you. Don't worry about it. Let's try to decode this particular problem. So, assume that you work as a quality test. You work as a, let's say, as a scientist in the quality test department of this milk producing factory or milk packet factory. So you work as a scientist in the quality test department, and on the daily basis, let's say this factory on the daily basis is producing 1 lakh milk packet. 1 lakh milk packets. So on the daily basis, this factory is producing 1 lakh daily packet. Now as a scientist, it is completely impossible for you to test all the milk packet, right? So what is the correct procedure? We have already learnt about it. We will take a sample out of it. So let's say on the daily basis, you are taking a sample of 40 milk packet. So let's say I have just drawn a table on my screen. Let's say this represent the day in the month. So day of the month, and this represents the average milk quantity. So let's say on day 1, the average milk quantity. So on day 1, you sampled out 40 milk packets out of the population of 1 lakh milk packet that was produced on that particular day. You sampled out 40 random milk packets. After performing the test on all those 40 packets, the average milk content came out to be, let's say, 92.5. Then on another day, the average came out to be 92.7. On another day, the average came out to be, let's say, 8. On another day, the average came out to be, let's say, 92.27. And you have been doing this thing, let's say, for last 1 month. So let's say on day 30, so I'll just put ... in this table. On day 30, the average came out to be 92.66. Now, when you looked at the month average, the complete month average, the monthly average was 92.84. Now, this is what has been given to us. So, another day, let's say another month, another day, when you were testing 40 new milk packets, your average came out to be 92.7. 0.67. So I hope this complete picture is making sense. You have been doing the test for all the days from day 1 to day 30 from last 1 month, and the average was 92.84. And this is, let's say you can say that this is above the quality cutoff. But on one particular day, after testing this 14 new milk packets, the average came out to be 92.67. Now you want to perform the test to check if this number, the new mean, the new sample mean, is in the significance range, or is this number is 92.67 statistically significant or statistically same as 92.84 or not. So what we want to test is 92.67 statistically same as 92.84 or not. This is what we want to test. So if these two numbers are statistically same, then we will approve this batch of new 40 milk packets. If they are different, if they are statistically different, we will reject the complete lot because the milk content is less than the acceptance. This is what the complete scenario is. Now the number one thing that we will do is to formulate the null and alternate hypothesis. So my alternate hypothesis will be that the average is not equal to 92.84. Why I'm using 92.84 over here? Because that is my previous proven value. This is my initial value, right? Initial. Now null will be the average is equal to 92.84. Okay. Now please remember one thing. Whenever we have a not equal to sign, this basically means I have to perform the test which will be a two-tailed test. So let's quickly understand this part. If I'm having not equal to sign in my alternate hypothesis, then my rejection region, so what is rejection, what is acceptance, we will talk about it, don't worry, but my rejection region will be on both the side. So this is my rejection region, this is my rejection region. If I am having less than sign in my alternate hypothesis, then my rejection region will be on left side, this side. So just see the arrow. So the arrow is pointing on the left. So my rejection region is on the left. If I'm having greater than sign in my alternate hypothesis, then my rejection region will be on the right, which is on this side. So just see the arrow. Arrow is pointing towards the right. So my rejection region is on the right. Now since I'm having not equal to sign in my alternate, this particular test would be a two-tailed test. So this is known as a two-tailed test. This is known as a left tail. This is known as a right tail test. So this is my two-tailed test. So my rejection region is on the both end. I'll just highlight it. This is my rejection region and this is my rejection region. Now what we are going to do, we are going to find out this particular value, lower value and the upper value. Now I hope you guys remember that we have already done this using confidence interval estimation in inferential statistics. We have already found out the limit, the lower limit and the upper limit, right? So we have the average, so here we call this as a population average. So we have the average plus minus z times of sigma divided by root of n. Now what is going to be my z value? Now for that we have to use this significance level. Significance level, also known as alpha, is basically my area of rejection, which is 0.05. So out of the complete area, which is 1, 0.05 is the area of rejection. Now since I'm having area of rejection or rejection region, these are my rejection regions. Rejection region. This is also my rejection region. Since my rejection region is on both the end, I have to divide this significance or area of rejection by 2. So 0.05 divided by 2 will be 0.025. So from here to here, the area is 0.025. From here to here, the area is 0.025. Now what is the z value over here? What is the z value over here? We already know this, but let's quickly find out the z value at 0.025. So 0.025 over here, and the value is minus 1.9 and 6. Similarly, for the positive side, it will be plus 1.96. So this is minus 1.96 plus 1.96. Now using this, we will find out the lower value and upper value. So 92.84 plus minus 1.96, sigma which is standard deviation is 1.979 divided by root of 40. So we will get 92.286 comma 93.394. So here we will have 92.286. Here we will have 93.394. Now this is the range in which has been given to us, or which we have derived using the population mean. So now if my sample mean, this is my sample mean. If my sample mean lies between or maybe in the acceptance range, this is my acceptance range. Acceptance range. So if my sample mean lies in the acceptance range, we say that we fail to reject null. So 92.67 will lie somewhere between this over here, since it is lying in the acceptance range. So if sample mean lies in acceptance range, we conclude that we fail to reject null. Otherwise, if it is in the rejection region, if sample mean, so I forgot to write mean, false or lies in the rejection region, we reject null. We reject null. So as of now, what conclusion we will derive? The conclusion will be we fail to reject null. Why? Because the sample mean is within the acceptance region, or within the boundary which we have derived using the population mean. This is also known as the hypothesized mean. The reason hypothesized mean is because we hypothetically call it as a population mean, but it is not the true population mean. So if you are getting confused, just be very clear. This is a sample mean 92.67, 92.84 is my population mean, and using the population mean we have derived a range. If my sample mean fall within this range, we fail to reject null. If it is outside the range, we reject null. I hope this question makes sense. If it is not, let's take one more example. Now let's try to solve this particular problem, and I would advise all of you to pause this video and try to solve this problem by yourself, because we have already seen one example. You have to just follow the steps and try to solve this problem, and try to pause the video and just try to solve it by yourself. I assume that you guys would have solved it by yourself. If not, let's try to solve it. The question says, in a certain community, a claim is made that the average income of employed individual is $35,500. Now again, there is some initial statement which has already been proven that the average income is 35,500. So this is my initial statement. Initial statement. A group of citizens suspect that a value is incorrect and gather a random sample of 140 employed individual in a hope of showing 35,500 is not the correct average. The mean came out to be 34,325. So what the group of citizens did, they collected a sample of 140 people and they obtained the sample mean to be 34,325 with the population standard deviation. The population standard deviation. So this is not sample standard deviation. So here we have been given with the population standard deviation of $4,200. The alpha, what is alpha? The area of rejection is given as 0.10, which is 10%. Now let's start with the formulation of the hypothesis. My alternate hypothesis is that the average is not equal to 35,500 because 35,500 is the initial value or initial state. So group of citizens wants to prove that 35,500 is not the correct average. So that's my alternate. Null will be opposite of this. Mean is equal to 35,500. Now what is my second stage? I will find out the lower critical value and the upper critical value. So here is my normal distribution. Since I am having not equal to sign in my alternate hypothesis, it is the two-tailed test. My area of rejection is on both the end. So this is also area of rejection and this is also my area of rejection. Now we have to find out the lower critical value and the upper critical value. Before that, we are given with the alpha of 0.10. Since I am having rejection region on both the ends, my alpha will be divided by 2. So 0.1 divided by 2. So this will be 0.05 from here all the way up to here. And this will also be 0.05. So what is the z value over here? Again, we will use the z table. So we have to look at 0.05. So 0.055. Okay, over here. Maybe we can take this one or maybe this one. So minus 1.64 or 65. You can take any one. So I'll go with minus 1.64. So this is minus 1.64. This is plus 1.64. Now I have the z value. I have all the values. Let's calculate the range. Mean plus minus z times of sigma divided by root of n. My mean is 35,500 plus minus 1.64. Standard deviation is 4,200 divided by root of 140. So the range would be 34,917.76 comma 36082.24. So this value, lower value, is 34,917 and the upper value is 36082. Now where my sample mean is lying at? 34325. So my 34325 will lie somewhere over here, right? 34325 in the acceptance region. Since it is falling in the acceptance region, we conclude that we fail to reject null. And that basically means the claim that was made was correct, which basically means this null is actually true. Now I'm just saying we fail to reject null, but maybe because the sample size was less, or because the sample collection process was biased, due to which the citizens were not able to prove that 35,500 is a wrong average. But as of now, using the test result, we failed to reject null. I hope this makes sense. Now here we have one more example. So we have seen two examples where we used two-tailed test, where the rejection region was on both the end. But now let's take one example where I'm having a one-tailed test, either left or right. So the question says, suppose the scores on the SAT, so SAT is one of the examination, form a normal distribution with mean 500 and standard deviation 100. The school counselor has developed a special course designed to boost SAT score. A random sample of 40 students is selected. So we have a sample of 40 students, and the sample average came out to be 544 after they have gone through the course and they have attempted the SAT examination. The question already states that the SAT score is having a normal distribution with mean 500 and a standard deviation of 100. So this is my population parameter. You may assume these are the population parameters. Now, does the course boost the score? Does the course boost the score? So my alternate hypothesis is, does the average is greater than 500? Because if the course boosts the score, it should be greater than the population average, which is 500, right? Null is, it is less than or equal to 500, right? Now greater than 500 basically mean it is, the arrow is pointing on the right side, so it is a right tail test. So my rejection region will be on the right end. This is my rejection region. Now what we have to do? Again, we have to find out the z value over here. So let's find out the z value over here. Now to find out the z value, the area of rejection alpha is given as 1%, which is 0.01. So this area from this point all the way up to the end is 0.01. So what is the area from this point all the way up to this point? It will be 0.99. So now we will use the z table to find out the z value at the AUC of 0.99. So let's use the z table. So 0.99, what is the z value? So either we can go with this value or this value. So this is 2.32 or 2.33. So I'll go with 2.32. So z value is 2.32 and this is plus. Now let's apply the formula, mean plus z times of sigma divided by root of n. Remember, the lower value will now be minus infinity. We have to just find the upper value. So mean is 500 plus 2.32. Sigma is, which is the standard deviation, is 100. So this will come out to be 36.6. So the total is 536.6. So this value over here is 536.6. Now, where my sample mean is lying at? My sample mean was 544. 544 will lie on this side, right? On the rejection side, this side. So this will be 544. So since my sample mean is lying at the rejection region, we conclude that we reject null. So if I reject null, that basically means the course does increase the SAT score. The course does increase the SAT score. Now please remember, this statement is based on this particular sample. I am not saying it will always increase the SAT score. Based on this sample, the conclusion is that course does increase the SAT score, but it might be because of some uncertainty. It might be because when we were when we were selecting the students, we have only selected the intelligent students with higher IQ, and that is the reason we obtained the average which is greater than the population average. So it might be because of the uncertainty also. So that is the reason we say we reject null. We are not saying we accept alternate. We will not say that. I hope now the thing is making more sense. So now let's talk about t-test. We have already seen z-test in very much detail. We have solved 3 problems. Now let's talk about t-test. And before we jump into solving few problems using t-test, let's first of all understand when to use a t-test. So we have already talked about z-test. Now let's write down the conditions for t-test. So I will write it over here, t-test. So we use t-test condition number 1 when the number of observations in the sample is less than 30. So the number of observations is less than 30. This is my first check. The second check is population standard deviation is unknown. The third check is the sample has been taken out from a population which is known to be normally distributed. The sample has been taken out from a population which is known to be normally distributed. Now, what is the meaning of the sample has been taken out from a population which is known to be normally distributed? So let's say I take example of income. I know that in India the income is normally distributed. Now if I take a sample of 5 people, now this sample will satisfy the t-test parameters because I know that it has been taken out from a population which is normally distributed. The number of observations in the sample are less than 30 and the population standard deviation is unknown. So I don't know what is the standard deviation of the income in my Indian population because the population is really large, right? So before we apply t-test, we have to check these conditions, we have to check these parameters. Now let's solve a problem to understand this. As I've already told you that t-test can be performed, or there are 3 types of t-test based on the problem statement. So let's try to understand them very briefly about what kind of problem statement satisfy which kind of t-test. Now there can be 3 type of t-test. One sample t-test, paired sample t-test, and finally the independent sample t-test. So regarding one sample t-test, we try to compare the mean of single group with known mean. Now if it is not making sense, don't worry. When we will be solving a problem, then I'll better explain you this. Paired sample t-test. Here we compare the mean of the same group at two different time. So at 2 different time. In independent sample t-test, we compare the mean of two different groups. Now, if it is not making sense, don't worry. We will take example of each one of them and then it will make more sense. Let's start with one sample t-test. So a DS lawn service advertised that they can maintain your lawn at an average cost of $35 per month. Now this is what their proven value is, the initial value that they have given. Assume the cost to be normally distributed. Now this is a very important sentence. The population is normally distributed, that has been given to us. A random sample of 18 DS customers shows the average of 32.50. So we have taken a sample. The sample is having the mean of 32.50 and the sample standard deviation to be 18.10. Now we know that this sample has been taken from a population in which the cost was normally distributed. Cost was normally distributed. So first of all, let's check whether this question or this particular problem satisfies the condition of t-test or not. The very first condition is the number of observations in the sample should be less than 30. Here my n is 18. So yes, first condition is satisfied. Second condition is the population standard deviation is unknown. Yes, we do not know the population standard deviation, but we know the sample standard deviation. And the third one is the sample has been taken out from the population which is normally distributed. So this particular sample has been taken out from a population where the cost was normally distributed. So all the three conditions are satisfied. Let's try to see the procedure now. Number one, we have to formulate the hypothesis. So my alternate hypothesis would be that the average cost is less than 35. So this is what we want to test. So average is less than 35. Null will be average is greater than or equal to 35. So this is my null and alternate hypothesis. Again, since I am having less than sign in my alternate, it is a lower tail test. So lower tail test. Now we will find out the T critical. Now T critical formula is similar to Z value, x minus mu divided by sigma divided by root of n. I hope you guys remember the Z value formula when we were talking about the Z scaling. The Z value formula was x minus mean divided by sigma. Now here I am using sigma divided by root of n is because this distribution is a sampling distribution and the standard deviation of the sampling distribution is given as sigma divided by root of n according to the central limit theorem, right? Now what is x? X is my sample mean, which is 32.50. Mu is my population mean, which is 35 divided by sigma 18.10 divided by root of 18. What is the value? You guys can quickly calculate it. I have already calculated it. So this will be minus 1.30. Sorry, there is a one correction. This is not T critical. This will be T estimated, TE. So T estimated is minus 1.30. Now we will find out the T critical, which is calculated using the T table. And T table requires your alpha, which is given as, so okay, I haven't written alpha, so let's assume alpha to be 0.05. So alpha is 0.05 and degree of freedom. Now degree of freedom is given as n minus 1. But what is degree of freedom? What is degree of freedom? So let's understand degree of freedom. Now let's say there are three people, 1, 2 and 3. These are the three people, and let's say these are A, B and C, and this is Sumit. Now what I'm asking ABC to do, I'm asking ABC to choose one number in such a way that the total is 10. Now let's say, so let's write down ABC and the total. Now we already know that the total in all the cases would be equal to 10. So let's say A has chosen 5, B has chosen 3. Then C is bound to choose 2. Let's say A has chosen 5, B has chosen 5. Then C is bound to choose 0. Let's say A has chosen 1, B has chosen 1. Then C is bound to choose 8. Now you guys can see that the third component or the third data point in my summation is not free to choose a value when we already know the total. So there are only two values A and B which are free to choose any value of their choice, but C is always bound. C is always bound to choose a value that is left out. So degree of freedom talks about how many observations in your data are free to choose a value. The number of observations in the data that are free to choose a value. Now here, since we know the sample average, since we already know the sample average, the degree of freedom will always be n minus 1, because there will be always one value which will be bound to choose a value that can make the average to come out to be what we are given with. So here degree of freedom will be n minus 1. N is 18, so 18 minus 1 is 17. Now we will use the t table with these two parameters to find out the t critical value. So let's use the t table. So this is a one-tailed test with the significance of 0.05 and the degree of freedom to be 17. So here, so correct value is minus 1.740. So T critical is minus 1.740. Now I'll quickly delete this because I do not have to write this first. First of all, we will write the T critical minus 1.740. Now where this minus 1.30 will lie? T estimate. T estimate will lie, let's say, so minus 1.3. Minus 1.3 will lie over here, right? So this is my rejection region. This is my rejection region, which is below the T critical value, and my T estimated is beyond the T critical. So this is the boundary T critical, and this is my T estimate. Now since T estimate is on the acceptance side, we say that we fail to reject null, which basically means that this statement, it is greater than or equal to 35, that basically means those people who were doubting, who were having the doubt regarding this DS launch service, they were actually correct, that based on this sample we can conclude that the average cost that this DS launch service charges for maintaining your lawn is not 35 or less than 35, it is more than 35. I hope this is making sense. This was one sample t-test. One sample t-test. Now the reason it was one sample t-test is because we have one group, we have a known mean which is 35 and we are comparing the sample mean with the known mean. So this is one sample t-test. Now in the paired sample t-test, this is the example of paired sample t-test. Here we compare the average of one group at two different time. So here you can see that we have before result and after result. Let's try to solve this problem to better understand this. So here in this question, we are given with the problem statement states that a study was conducted to determine the effectiveness of a weight loss program. The table shows before and after weight of 10 individuals. Does the program was effective in reducing the weight? We have to test at a significance of 5%. Now if we logically think about this question, the program will be called effective when the difference, what is the difference? After minus before. When the difference is negative. So let's calculate the difference. I have already calculated it, so I'll just fill the table. So 169 minus 185 minus 16 minus 5 minus 13 minus 1 minus 31 plus 3 minus 28 minus 22 plus 5 and minus 23. Now these are the differences. If this difference is negative, that basically means the person obtained or the person achieved the weight loss. If it is positive, that means the person achieved the weight gain. So if I look at this observation of individual number 6, the person was having a weight of 168, it increased to 171. So the person gained three units of weight, while this person whose weight was 218, now it came to 195. So this individual achieved a loss in the weight of 23 units. Now I will call this program effective if the average difference is below 0, right? Below 0 means negative. So my null alternate hypothesis will be the average is less than 0, because initially I will consider that the program is not effective. Initially I will consider that the program is not effective. So initial statement will be the average is either greater than or equal to 0. So assume that this is a number line of differences D, where if my average difference is 0 or above this is 0 or positive, then my program is not effective. If it is negative, then my program is effective. So these are my null and alternate hypothesis. Now what we have to do, this is my sample. So I need the sample mean, so mu x. My average of differences, so I'll just write mu d, the average of differences. I have already calculated it. You guys can use Excel for this quick calculation. So the average difference is minus 13.1 and the standard deviation of the sample is 13.02. This is my sample statistic. Now I will calculate the t estimate. T estimate is x minus mean divided by sigma divided by root of n. My x is minus 13.1. My minus 13.1. Population mean is 0. Population mean is 0, which we have assumed that there is no change, there is no gain, there is no loss, 0. Sigma is 13.02 divided by root of n. N is 10. Now this will came out to be minus 3.18. Now using the alpha, which is 5%, so 0.05, and degree of freedom, which is n minus 1, which is 10 minus 1, which is 9, I will find out the T critical using the T table. So let's quickly do this. So degree of freedom, so this is a one-tail test, significance level 0.05, degree of freedom to be 9. So here we have the value 1.833. 1.833. Now since it is a lower tail test, because I am having lower sign or less than sign, so the value T critical will be, let's say this T critical is minus 1.833. Now where this minus 3.18 will lie? Minus 3.18 will lie over here, T estimate. Now since it is lying on the rejection region, we conclude that we reject null, which basically means yes, based on this sample, the program was actually found effective. So yes, based on this sample, the program was found to be effective. Now here you can see that the reason we call this as a paired sample t-test is because we were having the same group, but at two different time, before and after, same set of people before and after. So paired sample t-test, we are comparing their average or the average difference. Now we have independent sample t-test, which basically means now we have two different group A, group B, and we have to compare them. So let's see this example. So this is the example of independent sample t-test. And in this particular test, we are having two different groups. Now if you read the question, it says, let's consider an example where we want to compare the effectiveness of two different study techniques. 30 random students are selected. They were divided into two groups. Group A was subjected to technique A. Group B was subjected to technique B. Now please remember, I'm having total number of students to be 30, where we have divided them into two equal groups. So that basically means group A consists of 15 students, group B consists of 15 students, group A consists of 15 different students, group B consists of different students. So these two groups are not having any association between them. They are two different groups. Now I want to compare whether technique A and technique B, whether they are same or different. That's what my test is, whether they are same or whether they are different. So my alternate hypothesis will be average of A is not equal to average of B. My null hypothesis will be average of A is equal to average of B. So my null hypothesis is that I'm initially assuming that these two techniques are same, where what I want to prove that these two techniques are different. So that's my null and alternate hypothesis. Now we will follow the same procedure, but there will be a minute difference in the T estimate. The formula for T estimate is x1 average minus x2 average minus mu1 minus mu2 divided by square root of sigma 1 square divided by n1 plus sigma 2 square divided by n2. So here in my table I am already given with mu1 and mu2. So let's fill that table, fill this formula. Mu1 is 84.07 minus 78.23 minus mu1 and mu2. So we are assuming that mu1 is equal to mu2. So this will come out to be 0. Since we are assuming, my null hypothesis is that these two average, the population average, are same. So mu1 minus mu2 will always be 0. Then square root of sigma 1 square. So 3.87 to the whole square divided by n1, which is 15, plus 2.61 to the whole square divided by 15. If I solve this, we will get 3.02. This is my t estimate. Now this is a two-tailed test, right? This is a two-tailed test because I am having not equal to sign my alternate hypothesis. Two-tailed test. We have not given with alpha. Let's assume alpha to be 0.05. So this portion will be 0.025. This portion will be 0.025 and both are my rejection region. Now I want to find out T critical, which is this point, T critical. Again, we have to use alpha, which is 0.025, and we need degree of freedom. Now in the case of independent sample t-test, the degree of freedom is given as n minus, so degree of freedom is given as n1 plus n2 minus 2. So my n1 is 15 plus 15 minus 2, which is 27. So I'll be using alpha as 0.05, alpha as 0.025, T critical as 27 to obtain the T critical value using the T table. Let's do that. So I'm now in the two-tailed test and we have to look at 0.025. So two-tailed test, alpha is given as 0.05, right? Alpha is given as 0.05. We can use, so what I have done, since I have divided it by 2 in my T table, it gives from the left, it gives the T critical value from the left. So if I go with 0.025 from the left, I will get this value. And if I go from this value to this, if I have to find out this value, it will be 0.95. So let's use one tail test, or if you want to use, you can use two tail test at the alpha of 0.05. We can use any of one of them. For avoiding any confusion, let's use two tail test at a alpha of 0.05. So let's look into that. So two tail test, alpha is 0.05 and we are given degree of freedom as 27. This is 2.052. So my T critical is minus 2.052 and this will be plus 2.052, right? Because always they are complementary to each other. 3.02, where this will lie? 3.02 will lie somewhere over here on this rejection region. This is T estimate. Since it is lying on the rejection region, we say that we reject null. And when we reject null, basically mean they are not same, they are different. So based on this particular sample, we conclude that these two techniques are different from each other. So based on this sample, we conclude that these two techniques are different from each other. This is what independent sample t-test is. Now we have completed our discussion on hypothesis testing. So we have talked about how we can perform. So we started our discussion with how to formulate the hypothesis. Then we talked about the two kind of test, z-test and t-test. Within z-test, we looked at two methods, z-value method, p-value method. Within t-test, we looked at the various types of tests which are based on various types of problem statements. One sample t-test, paired sample t-test, independent sample t-test. And we solved a variety of problems also to make our understanding more concrete, right? Now we are going to talk about a topic which is known as error in hypothesis testing. As I talked initially that there might be some uncertainty that my test goes wrong, right? Since this is a test which we are performing on the sample, we can never be 100% sure that what result my test is providing us or the conclusion that we made from the test is always going to be 100% true. Let's say my test concluded that uh, we reject null, or let's take one example. In this particular example we have rejected null, right? What if this was actually not true? So based on these two samples we concluded that we reject null, but what if in reality overall, so as of now we have taken a sample of 15 students, and just because of the sample of 15 students we concluded that we reject null. But what if in reality, if I take a much bigger sample, in reality this is not true, this is not true, both techniques happen to be same, then that is known as the error in hypothesis testing. So how we can avoid this error? Before we can avoid this error, we have to be very much clear with what kind of error hypothesis testing can lead us, or what kind of errors we can encounter while performing hypothesis testing. Let's try to understand that now. Before we talk about this particular problem, so I have written one condition or I have written one problem statement. Let's try to summarize what are the various error we can encounter while performing hypothesis testing. So we can summarize the type of error in a 2 cross 2 matrix. This is the reality, and this one is the test result or hypothesis test result. Hypothesis test result. Now there can be 4 type of scenarios. So in reality the null hypothesis was true, so H0 was true and H0 was false. Here we rejected H0 and we failed to reject H0. Now when H0 was false and we rejected H0, this is a good thing, right? So this is my correct conclusion. So I'll write correct over here. This is correct. When my H0 was true and we failed to reject H0, this is also correct. Now where is the error? Error is in these two cases. When my H0 was true in reality, so in reality, let's say, in reality, I know that the program is not effective. So in reality, program is not effective. But based on the sample, we concluded that program is effective. So this is a wrong estimation or wrong result. So this is known as the type 1 error. Type 1 error. And this is represented by alpha. So alpha, which is area of rejection in all the questions that we have solved, is basically the probability of type 1 error. What is the probability that I will commit the type 1 error is basically given by alpha. And this is known as the type 2 error. When your H0 was false, so in reality my null hypothesis was wrong. So in reality, let's say the program is not effective. So in reality, let's say program is effective and we fail to reject H0. So we concluded that program is not effective. That's a type 2 error. If this is confusing you a lot, don't worry. Now let's look into examples. Let's look into this example. city had an unemployment rate of 9%. So what is my null hypothesis? My null hypothesis is that the city had an unemployment rate of 9%. Group of citizens thinks that the unemployment rate is different from 9%. So alternate is average is not equal to 9%. Null is average is equal to 9%. This is my null and alternate hypothesis. Now if I commit type 1 error, then what will be the case? So type 1 error means H0 is true in reality, but we reject H0. So what is the meaning of this? So in reality, unemployment rate was 9%, but we concluded that it's not 9%. We rejected H0, right? What is type 2 error in this case? Type 2 error will be that in reality, unemployment rate was not 9%, but we concluded that it was 9%. So we failed to reject null. We failed to reject null means we concluded that the unemployment rate is 9%, but in reality it was not 9%. Now, as of now, I am not talking about which one is good, which one is bad. I am just talking about how to identify the type 1 and type 2 error. Just remember that you have to just keep this particular table or this matrix in your head so that you can formulate type 1 error and type 2 error. Let's take one more example. A city planned to construct a new parking area. They planned to survey a sample to see if there is a strong evidence that the proportion is interested in new parking area. If it is more than 40%, then the government will consider building a new parking area. So if the proportion, so let's say government has taken a sample of different individuals from the population, and if this sample results in 40% interested. So let's say 40% of the people in this sample are interested in the new parking area in the city, then the government will propose a new parking area in the city. So what is the null and alternate hypothesis? So my alternate hypothesis is that the average is greater than 40%, because this is what we were trying to prove. Null is the average is less than or equal to 40%. So initially my assumption is that no one is interested. My initial assumption is no one is interested. I am trying to prove that more than 40% people are interested in the sample. Now what is my type 1 error? Type 1 error is basically reject H0 when H0 is actually true. So type 1 error will be reject H0. We will reject H0 basically mean we concluded that more than 40% people in the sample or in the population are interested for the new parking area, while in reality in reality less than 40% people were interested. So this is my type 1 error. What is type 2 error? Type 2 error is basically we fail to reject H0, when H0 was actually false. So what is the conclusion for this? We failed to reject H0. So we concluded that less than 40% people are interested for the new parking area, while in reality H0 was actually false. So in reality more than 40% people were interested. Now if I ask you, if let's say you are a government body and you are performing this test, which particular error is more problematic for you as a government body? As a government body, type 2 error, you can see that it is problematic for us because we have concluded that less than 40% people are interested in the new parking area, which basically mean we will not build the new parking area. So the consequence of the type 1 error would be government will choose not to build the new parking area when it was actually required. When it was actually required. So what is the end problem for this, or major consequence that will happen to the government? Well, people will not be happy with the government, right? So people will not be happy with the government, right? What is the consequence of type 1 error? Now the consequence of type 1 error is that the government will build the new parking area when it is not required. So government will end up building the new parking area when it is not required. And what is the consequence that government will be facing? Government will be investing some unnecessary amount from their budget in building up this new parking area, which will impact their budget. So impact in their budget. Now as a government body, you need to decide which particular error you want to reduce, because see, since we are doing hypothesis testing, since we are doing estimations, we cannot be free from error. There will be some kind of error, but you have to decide which error you are ready to bear or which error is less problematic for you. So if you are a government body, you have to decide whether you are ready to face the impact in your budget or whether you are ready to face that people will not be happy with you. Well, if I would be a government, I would not be taking up the type 2 error on me because I want my people to be happy. So I would do something with the budget. I would try to maybe cancel some ongoing projects or maybe cancel some new projects. But I don't want my people to be unhappy with the government, right? Let's take one more example to understand how we can adjust the alpha, because we know the alpha value, right? We can tuke the alpha value, we can increase or decrease the alpha value to increase the chances of type 1 error and reduce the chances of type 2 error. So you can assume that if I'm having a number line, then if I want type 1 error to be high, I can increase the value of alpha, and it will eventually reduce the type 2 error, the chances of type 2 error. It is like a number line, you can shift it. Let's see one last example. So employee at a hotel perform daily water tank quality test. Okay. To check if the water quality is good for the people to take bath and use it for toilet. Based on the test result, water supply is stopped for 3 or 4 hours to perform the cleaning process or for the cleaning process. If the test results are positive, the water supply is not stopped. Test at alpha of 0.05. Now in this question we are provided with the alpha of 0.05. What is the alternate hypothesis? Let's you guys can pause the video, think about it, and then you can maybe comment on the chat section. So now let's try to understand this question, and I hope you guys would have already guessed what is going to be the alternate and the null hypothesis. My null hypothesis would be that the water quality is fine. So water quality is fine, is good, fine or good. My null would be, my alternate would be water quality is not good, right? Now what is the type 1 error? The type 1 error is basically that we reject H0 when it was, so let's write it down. We reject H0 when H0 was actually true in reality, right? So what is the meaning of this? We reject H0. So we rejected that water quality is fine when H0 was actually true. So what will happen? So we will close the water supply. We'll close the water supply when it was not required, right? What is type 2 error? Type 2 error is we fail to reject H0 when H0 was actually false. So what will be the consequence for this? So we failed to reject H0. So which basically means we concluded that the water quality is good when H0 was actually false. So that basically means we will not close the pool, or we will not close the water supply, or maybe let's not write let's write the water supply was not stopped. Water supply was not stopped when the water quality was bad. Water quality was bad or not good. Now, which one is more problematic? So if you are a hotel owner, then which one is more problematic for you? So if I go with the type 1 error, we have to close the water supply when it was not required, which basically means we will clean, or your employee, or the maybe your the people who clean the tank, they will perform the cleaning process, but there will be a stoppage of water supply for 3 to 4 hours. Maybe this is not a big problem, because maybe you can decide the window of afternoon, and then the water supply can be stopped for 3 to 4 hours, and it will not impact the service, right? So when you have to stop the water supply, you have to also think that it may impact the service, but it will eventually not going to harm you in a very large scale, because you can choose the window in the afternoon when most of the people are either out of the hotel or maybe involved in some other activities. They would not be using the bathroom, right? What is the consequence of type 2 error? Water supply was not stopped when the water quality was bad. Now, this is a more problematic condition. Let's say somebody is having a sensitive skin and that person is staying in your hotel. And if you do not clean the water, and let's say that person has taken bath in the contaminated water, the person can attract some kind of disease which can eventually land your hotel into a big problem, right? So type 2 error is definitely very problematic for you. Now we have already learned that alpha is the probability of type 1 error. So alpha is the probability of committing type 1 error. So now if I increase the value of alpha, there are more chances that I will commit type 1 error, but it will reduce the chances of type 2 error. So right now my alpha value is 0.05. If I increase this to 0.10, then what happened? I increase the probability of type 1 error. So let's say this is type 1 error. I increase the probability of type 1 error, so it will reduce the probability of type 2 error. And this is what you should do. So why we were talking about this particular topic? As a data scientist, let's say you are performing hypothesis testing. It is very important for you to carefully decide the value of alpha, and you can only decide the correct value of alpha by understanding the consequence of type of error. So let's say in this particular condition, if you are the data scientist working for this hotel chain, then you would eventually use the value of alpha to be on the higher side, so that the probability of committing type 2 error can be lowered down, and it is fine if I commit type 1 error, because as we have already seen, the type 1 error is something which is manageable, but type 2 error is something which is not manageable. I hope this makes sense. So this was all about this particular video. I hope this module was informative and really useful for all of you. If you like this video, share it with your friends, give this video a big thumbs up, and don't forget to subscribe to our Scalers YouTube channel.